The universe has been here for a very long time. In the roughly 13.8 billion years since the earliest moments of existence, space has expanded, matter has gathered, stars have formed and burned and collapsed. Galaxies have drifted apart across distances so vast they resist imagination. And through all of that, through billions of years of change and transformation, the universe has continued. It has persisted, but nothing persists forever. And among the deepest questions that cosmologists and physicists have spent generations exploring is this one. How does it all end? Tonight, we are going to sit with that question for a while. We will explore what modern physics tells us about the long-term fate of the universe. Not in dramatic terms, but carefully and slowly, the way the universe itself moves through time. We will look at three major theories: heat death, the Big Rip, and the Big Crunch. We will consider what each scenario means, what conditions would need to be true for each one to occur, and what the universe might look and feel like across the unimaginable stretches of time that lie ahead. Welcome to Sleepy Time Universe, where we explore the cosmos at a pace designed for rest and reflection. Get comfortable. We have a long and peaceful journey ahead. The question of how the universe ends is, in some ways, the largest question a human mind can hold. It requires us to think not in years or centuries, but in timescales so vast they make our entire recorded history seem like a single breath. It asks us to consider the nature of energy and entropy, the behavior of dark energy across billions of light years, and the ultimate fate of every atom and every particle that has ever existed. And yet, despite the scale of the question, the way physicists approach it is patient and methodical. They observe, they measure, they build models, they follow the mathematics where it leads, even when it leads somewhere difficult to picture. We will follow that same path tonight. Slowly and without hurry, we will move through the science of endings, pausing wherever a concept deserves more time, returning to earlier ideas when it helps to revisit them, and allowing space for the kind of quiet reflection that only comes when we consider something truly immense. We will begin where any good exploration begins, not with the answer, but with the question itself. Human beings have been asking how things end for as long as they have been able to ask questions at all. Long before the tools of modern physics existed, before telescopes or spectrometers or the mathematics of general relativity, people looked at the sky and wondered about permanence. Ancient cultures built cosmologies that described worlds with beginnings and endings. Some imagined a great fire consuming everything. Others imagined a slow dissolving, a gradual return to the formless void from which everything had come. Still others believed the universe was cyclical, that endings were always also beginnings, that destruction and creation were simply two faces of the same continuous process. These were not scientific theories. They were stories built from observation and imagination, attempts to make sense of a world that seemed both vast and fragile at the same time. But they were asking the right questions. They were wondering about time, about limits, about what it means for something as enormous as the universe to come to an end. Modern cosmology asks those same questions, but with different tools. Instead of mythology and intuition, we now have the mathematics of thermodynamics, the observational data of deep space telescopes, and the theoretical frameworks of quantum mechanics and general relativity. The tools are more precise. The answers, in some ways, are more detailed, but they are also, in important ways, still incomplete. We do not yet know with certainty how the universe will end. What we have are scenarios, carefully constructed theoretical outcomes, based on what we currently know about the composition of the universe, the behavior of the forces within it, and the direction in which things appear to be moving. Each scenario is plausible given certain conditions. Each one depends on factors we are still in the process of measuring and understanding. The three most discussed scenarios in modern cosmology are heat death, the Big Rip, and the Big Crunch. Each one represents a different possible answer to the question of endings, and each one tells us something different about the nature of the universe itself. Heat death describes a universe that simply runs out of usable energy. It does not explode or collapse. It fades. Over timescales so enormous they dwarf anything we can easily picture, the universe slowly reaches a state of maximum entropy, a condition in which energy is distributed so evenly and in such degraded forms that nothing can ever happen again. No stars can form, no chemical reactions can occur, no information can be processed. The universe becomes a vast, cold, silent expanse in which nothing changes, because there is no longer any difference between one place and another, no gradient of energy along which any process can run. The Big Rip describes something more violent, though not in the way we typically imagine violence. In this scenario, dark energy, the mysterious force currently driving the accelerating expansion of the universe, does not merely continue its work at a steady rate. Instead, it grows stronger over time. As it does, it tears apart the structures of the universe on progressively smaller scales. First, galaxy clusters separate. Then, individual galaxies lose their cohesion. Then solar systems, then planets, then atoms themselves. The fabric of space expands so rapidly and so forcefully that even the bonds holding matter together at the subatomic level are eventually overwhelmed. The Big Crunch represents the opposite possibility. In this scenario, the expansion of the universe eventually slows and reverses. Rather than growing forever larger and more diffuse, the universe begins to contract. Over billions of years, everything pulls back toward everything else. Galaxies collide and merge. Temperatures rise. Density increases. Eventually, all the matter and energy in the universe is compressed into a single, unimaginably hot and dense point. A reversal of the Big Bang, a final collapse that brings everything to an end in a moment of almost incomprehensible intensity. These are the three main possibilities we will explore tonight. But before we can understand them fully, we need to understand the universe as it currently exists, its composition, its behavior, its history, and the forces that govern how it changes over time. It is worth pausing here before we go further to simply appreciate the scale of what we are discussing. The universe has already existed for nearly 14 billion years. That number is difficult to hold in the mind. If you compress that entire history into a single calendar year, modern human civilization would occupy only the last few seconds of the last minute of the last day. Everything we have built, every story we have told, every measurement we have made, all of it fits into a sliver of time so thin it barely registers against the backdrop of cosmic history. And the timescales we are about to consider, the timescales relevant to questions about how the universe ends, are in many cases vastly larger still. We are talking about time measured not in billions, but in trillions, quadrillions, and numbers so large they require scientific notation just to write down. Numbers that make the current age of the universe seem like the very first moment of a journey that has barely begun. This is part of what makes the study of cosmic endings so philosophically unusual. It is not just that the scales involved are large. It is that they are large in a way that fundamentally changes how we relate to the material. We cannot experience these timescales. We cannot observe them. We can only reason about them, carefully and patiently, using the laws of physics as our guide. And so that is what we will do. We will follow the physics. We will let it take us where it leads. And we will do so at the pace that this kind of thinking deserves, slowly, thoughtfully, with room for the ideas to settle. Another aspect of the question of endings that deserves attention is the emotional dimension. There is something that feels significant, perhaps even unsettling, about the idea that the universe has a finite future. Many people encounter this material and find themselves sitting with a quiet sense of weight. Not panic, necessarily, but something like the feeling of standing at the edge of something vast and unknowable. That response is understandable, and it is worth acknowledging. The universe ending is not an abstract puzzle. It is, in some sense, the ending of everything, every galaxy, every star, every possible future. And while that ending is so far away as to be practically irrelevant to any living creature, the idea of it touches something deep in how we think about meaning and permanence. But there is another way to hold this material, one that many scientists and philosophers have found more useful. Rather than experiencing the eventual end of the universe as loss, it is possible to experience it as context. The fact that the universe had a beginning and will have an end places us in a particular kind of story. It gives the present moment a kind of weight that pure permanence could never provide. We exist in the middle of something, in the midst of a universe that is still young, still active, still generating the conditions for light and warmth and complexity. The stars that exist right now are a relatively early development in cosmic history. The universe, on the timescales we are about to explore, is still in something like its infancy, and that is a remarkable thing to sit with. We will return to these reflective moments throughout the night. For now, let us move forward into the science itself, beginning with how cosmologists think about time on scales that no human being has ever experienced directly. Time is one of the most familiar things in human experience and one of the most difficult to define precisely. We live inside time. We experience it as a continuous flow, a movement from past to present to future that feels inevitable and constant. Clocks measure it. Memories carry it. Plans reach forward into it. From the moment we wake to the moment we sleep, time is the medium through which every experience moves. And yet, when physicists examine time closely, it turns out to be considerably stranger than this everyday experience suggests. At the scales relevant to cosmology, scales involving billions of years, extreme gravitational fields, and velocities approaching the speed of light, time behaves in ways that challenge our intuitions at nearly every turn. One of the first things that a student of cosmology must come to terms with is the sheer magnitude of the timescales involved. We have already noted that the universe is approximately 13.8 billion years old. To understand what that means, it helps to try building a sense of it incrementally. 1 year is a unit most people can feel. It is the time it takes for seasons to complete a cycle, for a child to grow noticeably taller, for certain plants to complete their entire life from seed to decay. 10 years is a decade, long enough to see significant changes in a person's life, in technology, in the shape of cities. 100 years is a century, roughly the span of a long human life, long enough to encompass 2 or 3 generations. 1,000 years is long enough to see languages change, empires rise and fall, landscapes alter. 1,000,000 years is harder to feel directly. It is longer than the entire history of anatomically modern humans. It stretches back past the earliest stone tools, past the emergence of our genus. A billion years carries us back further still, past the formation of multicellular life, back toward a time when the surface of the Earth was unrecognizable, when the oceans were different colors, and the atmosphere was composed of gases that would be poisonous to us today. 13.8 billion years takes us to the very beginning, to the hot, dense, rapidly expanding early universe from which everything else emerged. Now consider that the scenarios we are about to discuss operate on timescales of trillions of years, and in some cases far longer. A trillion is a million millions, 1,000 billions. When cosmologists discuss the very long-term future, they sometimes work with numbers expressed as powers of 10. 10 to the 14th years, 10 to the 40th years, 10 to the 100th years. These numbers become less about measurement and more about ordering, a way of placing different events in sequence across time so vast it cannot be directly imagined. This is one reason why cosmologists have found it useful to develop what is sometimes called a deep time perspective. Deep time is not simply an awareness that a long time has passed or will pass. It is a way of thinking that holds immense durations without collapsing them into something manageable. It treats billion-year timescales as having genuine structure, as containing events and processes and changes that are worth understanding on their own terms, even though no human being will ever observe them. The geologist James Hutton is often credited with developing an early version of deep time thinking in the 18th century, when he looked at layers of rock and understood that they represented millions of years of slow accumulation. His insight was not merely that the Earth was old, it was that immense time had a texture, that it was filled with process, with change, with history. Cosmologists have extended that insight to the scale of the universe itself, and to the future as well as the past. One useful tool that cosmologists use to organize their thinking about the long-term future is the concept of cosmic eras. Rather than describing the future as a single undifferentiated expanse of time, they divide it into broad periods defined by the dominant processes occurring within them. This framework was developed in detail by the physicists Fred Adams and Gregory Laughlin in the late 1990s, and it provides an elegant way to think about how the universe changes over almost incomprehensible timescales. In this framework, we currently live in what is called the stelliferous era, the age of stars. This era began roughly 100 million years after the Big Bang, when the first stars ignited, and it is expected to continue for roughly 100 trillion years into the future. During the stelliferous era, the dominant feature of the universe is the activity of stars, their formation from collapsing clouds of gas, their long periods of stable fusion, their eventual deaths as white dwarfs, neutron stars, or black holes. We are currently about 14 billion years into this era, which means, in terms of cosmic history, the stelliferous era is still relatively young. The universe has much more star formation ahead of it, many more cycles of stellar life and death, many more billions of years of the kind of activity that has characterized the universe as we know it. Following the stelliferous era comes what Adams and Laughlin call the degenerate era. In this period, star formation has largely ceased because the gas and dust from which new stars form has been consumed or dispersed. The universe is dominated not by burning stars, but by their remnants, white dwarfs, neutron stars, and black holes. These objects cool and dim over unimaginable timescales. White dwarfs, which begin as dense, glowing embers, gradually radiate their remaining heat until they become black dwarfs. Cold, dark objects that no longer emit any significant radiation. The timescale for this cooling is itself enormous. longer than the current age of the universe by many orders of magnitude. After the degenerate era comes the black hole era, during which black holes are the dominant large-scale structures in the universe. Everything else has faded or been consumed. But even black holes do not last forever. Through a process predicted by the physicist Stephen Hawking, black holes slowly evaporate over timescales almost beyond description, releasing energy in the form of what is known as Hawking radiation, until, eventually, they simply cease to exist. And after the black hole era, after the last black hole has evaporated, comes what Adams and Laughlin call the dark era. This is, in their framework, the closest thing to an ending that the universe reaches under the heat death scenario. It is a vast, cold, nearly featureless expanse, populated only by the occasional subatomic particle, by photons of radiation so diffuse and low energy they carry almost no information, and by the slow, almost geological processes of matter at temperatures close to absolute zero. We will spend time in each of these eras as our journey continues. But first, it is useful to understand one more aspect of how cosmologists think about time, and that is the relationship between time and the expansion of the universe. The universe is not static. It has been expanding since its earliest moments, and this expansion is not simply a matter of matter moving outward through a fixed background of space. Rather, space itself is expanding. The fabric of the universe, the medium through which everything moves, is stretching, carrying galaxies apart from one another, not because they are moving through space in the conventional sense, but because the space between them is growing. This distinction matters for understanding the long-term future because it means that the rate of expansion, and whatever drives that expansion, is fundamental to determining which of our three ending scenarios comes to pass. If the expansion decelerates and reverses, a big crunch becomes possible. If the expansion continues at a steady or increasing rate, heat death or the big rip become more likely. And the key factor governing that behavior, the mysterious quantity known as dark energy, is one we will examine in detail in the next chapter. For now, it is enough to carry with you a sense of the framework cosmologists use when thinking about time at cosmic scales. They think in eras, they think in orders of magnitude, they think in processes that unfold across durations no single mind can hold, but which the laws of physics can trace with considerable precision. Time, in this view, is not just a backdrop against which events occur. It is itself a kind of structure, one that shapes what is possible, what is inevitable, and what remains genuinely uncertain about the future of everything. Let that settle for a moment before we continue. There is something quietly remarkable about the fact that human beings who live for perhaps 70 or 80 or 90 years have developed the mathematical tools to reason about events billions of trillions of years in the future. The laws of thermodynamics and quantum mechanics, discovered through careful observation and experiment over the past few centuries, turn out to apply at scales their discoverers could never have imagined. They are, in a sense, a kind of time machine, not one that carries us physically into the future, but one that allows our understanding to reach there carefully and with appropriate humility, ahead of our physical presence. This is one of the things that makes cosmology such a deeply human endeavor. We are a species that asks questions larger than our own lives. We want to know not just what is happening now, but what will happen, what must happen, what the laws of nature demand across all the time that remains. It is a form of curiosity that has no practical application in the ordinary sense. Knowing how the universe will end does not help us grow, food or build shelter or navigate our daily lives. But it does something else. It places us. It gives us a sense of where we stand in a story far larger than ourselves. And that, in its own quiet way, is enormously valuable. We will continue that placement now, moving from the broad framework of cosmic time into the specific physical phenomenon that currently governs the large-scale behavior of the universe, its expansion, its acceleration, and the dark energy that drives both. One of the most consequential discoveries in the history of science happened in the 1920s, when astronomers began to notice something unexpected in the light coming from distant galaxies. The phenomenon they observed is called redshift. When a light source moves away from an observer, the wavelengths of the light it emits become stretched, shifted toward the red end of the spectrum. This is the optical equivalent of the Doppler effect, the same principle that causes the pitch of a passing siren to drop as it moves away from you. By measuring the degree of redshift in the light from distant galaxies, astronomers in the 1920s could determine how fast those galaxies were moving relative to Earth. What they found was striking. With a few exceptions among galaxies in our immediate neighborhood, nearly every galaxy they examined was moving away from us, and the farther away a galaxy was, the faster it appeared to be receding. This relationship between distance and recession velocity was formalized by the astronomer Edwin Hubble, and it became one of the foundational observations of modern cosmology. What Hubble's observations implied, when combined with the mathematics of Albert Einstein's general theory of relativity, was that the universe itself was expanding, not in the sense that galaxies were flying outward through a static container of space, but in the more fundamental sense that the space between galaxies was growing, stretching. The distances between objects were increasing not because the objects were moving in the conventional sense, but because the medium in which they existed was expanding. This was a radical idea. For much of human history, the universe had been assumed to be eternal and static, a fixed stage on which cosmic events played out. The discovery that it was dynamic, that it had a history, that space itself was changing, transformed cosmology from a largely philosophical endeavor into an empirical science with testable predictions and measurable quantities. One immediate implication of an expanding universe is that it must have been smaller in the past. If we run the clock backward, if we imagine reversing the expansion, we arrive at a point in the distant past when all the matter and energy in the observable universe was compressed into an extremely hot, dense state. This was the beginning of what we call the Big Bang, a term that is somewhat misleading because it implies an explosion in a pre-existing space, when in fact it describes the very origin of space, time, matter, and energy together. The Big Bang was not something that happened in space. It was the event from which space itself emerged. Everything we observe, every galaxy, every star, every atom, traces its origins to that initial moment of extraordinary density and temperature roughly 13.8 billion years ago. Since that beginning, the universe has been expanding and cooling. In the first fractions of a second, it was unimaginably hot and dense, filled with particles and radiation in near-perfect equilibrium. As it expanded, it cooled. Simple particles combined to form hydrogen and helium. Eventually, gravity pulled that hydrogen and helium together into the first stars, which burned and died and scattered heavier elements into space, from which new stars and planets could form. The expansion of the universe during this early period was, in some sense, a competition between two forces. On one side was the gravitational attraction of all the matter in the universe, pulling everything together, tending to slow the expansion and potentially reverse it. On the other side was the momentum of the expansion itself, the outward push inherited from the conditions of the Big Bang. For several billion years, it was not entirely clear which force would prevail. The universe contained enormous amounts of matter, and matter generates gravity, and gravity works to decelerate expansion. Many cosmologists in the middle decades of the 20th century believed it was quite possible that gravity would eventually win, that the expansion would slow, stop, and reverse, leading ultimately to the Big Crunch scenario we mentioned earlier. Then, in 1998, two independent teams of astronomers made a discovery that overturned these expectations entirely. They were measuring the brightness of a particular type of exploding star, a Type 1, a supernova, at very large distances from Earth. Type 1, a supernova, are useful to astronomers because they all explode with approximately the same intrinsic brightness, which means their apparent brightness in the sky can be used to calculate how far away they are. By comparing the distances calculated from brightness with the recession velocities calculated from redshift, astronomers can trace how the expansion of the universe has changed over time. What the two teams found was that distant supernovae were fainter than expected, which meant they were farther away than models had predicted. The universe had not been decelerating as gravity-dominated models suggested. It had been accelerating. The expansion of the universe was speeding up. This discovery was profoundly unexpected. For the expansion to be accelerating, there had to be some force acting against gravity on cosmological scales, something pushing space apart rather than pulling it together. This force, or energy, or whatever it ultimately proves to be, has been named dark energy. Dark energy is one of the most important and least understood concepts in modern cosmology. We know it exists because we observe its effects. We know it accounts for approximately 68% of the total energy content of the universe, but we do not know what it is, where it comes from, or how it will behave in the future. The simplest description of dark energy treats it as a property of space itself, a kind of baseline energy that empty space possesses independent of the matter or radiation within it. In this view, as the universe expands and more space comes into existence, the total amount of dark energy increases proportionally. This is what is called a cosmological constant, a fixed energy density associated with the vacuum of space. If dark energy is a cosmological constant, then its influence on the expansion of the universe will continue at roughly its current level indefinitely. The universe will keep expanding, keep accelerating, and the ultimate destination will likely be heat death. The slow, cold, quiet ending we will explore in detail later. But dark energy might not be a simple constant. It might be a dynamic field, something that changes over time, either growing stronger or weaker as the universe evolves. Different behaviors of dark energy lead to different ultimate fates. And this is one reason why the question of the universe's ending remains genuinely open. Our ability to determine which fate awaits us depends in large part on our ability to characterize dark energy more precisely, which is an active and ongoing area of observational cosmology. One useful way to think about dark energy and its role in the fate of the universe is in terms of something physicists call the equation of state parameter, often represented by the letter W. This parameter describes the relationship between dark energy's pressure and its energy density. If W is equal to -1, dark energy behaves as a cosmological constant in density over time, neither growing nor diminishing as the universe expands. Under these conditions, the expansion of the universe accelerates, but at a finite and manageable rate. Galaxies separate from one another over billions of years, but the fundamental structures of matter, atoms, molecules, planets, stars, remain intact indefinitely. The universe heads toward heat death, if W is less than -1. If dark energy has what is called a phantom energy behavior, then the energy density of dark energy actually increases over time as the universe expands. This counterintuitive situation leads to runaway acceleration, with the rate of expansion growing faster and faster until it overwhelms all other forces. This is the Big Rip scenario. The expansion eventually becomes so rapid that even atoms are torn apart by the accelerating fabric of space. If W is greater than -1, if dark energy weakens over time, then the acceleration of expansion might slow and eventually cease. Depending on how much it weakens and how much matter the universe contains, gravity could potentially regain dominance and reverse the expansion, leading toward the Big Crunch. Current measurements place W at very close to -1, which is consistent with a cosmological constant. But the measurement uncertainties are large enough that values slightly above or below -1 remain possible. This is why the question of the universe's fate has not been definitively settled. We are essentially trying to determine, from our position in the early universe, how a quantity we cannot directly observe will behave over timescales billions of times longer than anything we have yet measured. It is, in a sense, one of the most ambitious extrapolations in all of science. Let us pause here and reflect on what we have covered so far. We began by noting that the universe has been expanding since its earliest moments, a discovery made through the observation of galactic redshift in the early 20th century. We trace the implications of that expansion back to the Big Bang, the origin of space, time, and matter. We noted that for much of the universe's history, the expansion appeared to be decelerating under the influence of gravity. And then we arrived at the unexpected discovery of 1998. The expansion is accelerating, driven by a form of energy we call dark energy, whose ultimate nature and long-term behavior remain uncertain. This uncertainty is not a failure of science. It is an honest reflection of where our knowledge currently stands. The measurements required to precisely characterize dark energy push the limits of what is technically achievable. New observatories and new measurement techniques are being developed specifically to address this question, because the answer, the value of W, and whether it changes over time, determines the ultimate fate of everything. There is also something philosophically interesting about the relationship between the expansion of the universe and the question of endings. The universe's expansion is, in one sense, its most fundamental ongoing process. It has been occurring since the beginning. It is built into the structure of space-time itself, and it is this process, more than any other single factor, that will determine how the story ends. In this way, the ending is written into the beginning. The conditions that produced the Big Bang, the amount of matter and energy created in those first moments, the properties of dark energy as a feature of the vacuum. All of these were set at the origin, or very close to it, and they have been unfolding ever since, across 13.8 billion years and counting, toward one of several possible conclusions. We are, in a meaningful sense, living through the middle of a story whose ending is already, in some physical sense, determined, even if we do not yet know what that ending is. That is a quiet and rather remarkable thing to consider. As we continue our journey through these ideas, we will move from the broad mechanics of expansion into the specific dynamics of dark energy, and from there into the three ending scenarios themselves. Each one will take some time to explore fully, because each one involves not just a final state, but an entire sequence of events, a long, slow progression through cosmic time toward whatever conclusion awaits. But we are in no hurry. The universe has plenty of time, and so do we. To understand the fate of the universe, we need to spend more time with dark energy, not because it is the only factor involved, but because it is the dominant one. It constitutes roughly 68% of everything the universe contains. It is the single most influential quantity in determining how the cosmos will evolve over the long term. And yet it remains, despite decades of study, genuinely mysterious. Let us begin with what we know. Dark energy was not predicted in advance of its discovery. It was inferred after the fact, a name given to whatever must exist in order to explain why the universe is accelerating. In that sense, it is similar to dark matter, which was inferred from gravitational effects before any direct detection was achieved. Both dark matter and dark energy are placeholders of a sort, labels for phenomena whose observational signatures are clear, but whose underlying nature remains unresolved. The simplest version of dark energy, the one most consistent with current measurements, is the cosmological constant. This concept was introduced by Albert Einstein in 1917, though under very different circumstances than those that give it relevance today. Einstein introduced the cosmological constant as a kind of counterbalancing term in his equations of general relativity. At the time, he and most other physicists assumed the universe was static, neither expanding nor contracting. But his equations, as written, described a universe that could not remain static. Matter and energy curve space-time, and without something to counteract this curvature on large scales, the universe would inevitably collapse under its own gravity. To prevent this collapse in his model, Einstein added a term to his equations that introduced a kind of repulsive energy, one that balanced gravity and held the universe in a stable, unchanging state. When Hubble's observations revealed that the universe was in fact expanding, Einstein abandoned the cosmological constant, reportedly describing it as the greatest mistake of his career. The expanding universe did not require a balancing term. It was already in motion, and the question became simply how that motion would evolve over time. Decades later, when the acceleration of the universe's expansion was discovered in 1998, the cosmological constant returned, not as a device to hold the universe static, but as a description of the energy apparently residing in the vacuum of space itself. Quantum field theory, the theoretical framework that describes subatomic particles and forces, predicts that even completely empty space should have a non-zero energy density. This is because quantum mechanics does not permit perfect stillness. Even in the absence of any particles, quantum fields fluctuate. They ripple with activity at the smallest scales, constantly creating and annihilating virtual particle pairs in a froth of quantum uncertainty. These fluctuations contribute energy to the vacuum, and this energy could, in principle, be what we observe as dark energy driving the expansion of the universe. There is, however, a significant problem with this explanation. When physicists calculate the expected energy density of the quantum vacuum using standard methods, they arrive at a number that is enormously larger than what is actually observed. The discrepancy is not a small one. Depending on how the calculation is performed, the predicted vacuum energy density is somewhere between 10 to the 40th and 10 to the 120th times larger than the dark energy density we measure. This is one of the largest discrepancies between theory and observation in all of physics, and resolving it remains one of the central unsolved problems of theoretical physics. This discrepancy suggests either that there is some mechanism we do not yet understand that suppresses the quantum vacuum energy to near zero, with a small residual amount corresponding to the cosmological constant, or that dark energy is something entirely different from vacuum energy, a new kind of field or phenomenon that our current theories do not adequately describe. One class of alternative explanations involves what physicists call scalar fields. A scalar field is a quantity that has a value at every point in space, but no directional component. Temperature is an everyday example of a scalar field. Some theorists have proposed that dark energy is a dynamic scalar field, often called quintessence, that pervades the universe and whose energy density changes over time as the universe evolves. Quintessence models come in many varieties, with different predictions for how dark energy behaves across cosmic time. Some predict that dark energy will weaken as the universe ages, which could allow gravity to eventually halt and reverse the expansion. Others predict it will strengthen, leading toward the Big Rip. Still others predict it will remain roughly constant, leading to heat death. Distinguishing between these possibilities requires measuring the equation of state parameter W with very high precision across a range of cosmic distances, and therefore across a range of cosmic times, since looking at greater distances means looking at an earlier universe. Current and upcoming observational programs, including the Euclid Space Telescope launched in 2023 and the Vera C. Rubin Observatory, now operating in Chile, are designed specifically to make these measurements with unprecedented accuracy. What these observations will likely reveal is not a final, definitive answer, at least not immediately, but they will tighten the constraints on W considerably, ruling out some scenarios and making others more or less probable. Over time, as the data accumulates, our picture of dark energy will sharpen, and with it, our understanding of which ending awaits the universe. For now, though, we must work with what we have, and what we have points clearly toward a universe whose expansion is accelerating, driven by a form of energy that shows no current signs of weakening. Under these conditions, the most likely long-term fate of the universe, the scenario most consistent with current observations, is heat death. We will explore that scenario in the next 2 chapters. But first, it helps to appreciate the immediate consequences of accelerating expansion, because they are already becoming visible in the universe today. As the expansion of the universe accelerates, distant galaxies are receding from us at increasing speeds. At sufficiently large distances, galaxies are already receding faster than the speed of light, not because they are moving through space at superluminal velocities, which would violate relativity, but because the space between them and us is expanding so rapidly that the effective recession velocity exceeds the speed of light. This is permitted within general relativity because it is space itself that is stretching, not matter moving through a fixed background. The practical consequence of this is that the universe has what is called a cosmological horizon, a boundary beyond which light emitted today will never reach us, because the space it must cross is expanding faster than it can travel. Objects beyond this horizon are permanently beyond our observational reach. Their light will never arrive. We cannot see them, communicate with them, or receive any information from them. Over time, as the expansion accelerates, this horizon draws closer in a certain sense, not physically, but in terms of the population of observable objects within it. Galaxies currently near the edge of what we can see will, over billions of years, recede past our horizon and disappear from observational reach forever. the observable universe will not shrink in absolute terms, but it will become increasingly isolated as the rest of the cosmos accelerates away. In 10 billion years or so, if the expansion continues on its current trajectory, the local group, the cluster of galaxies that includes the Milky Way and our nearest neighbors, will be essentially the only thing visible to astronomers in whatever civilization might exist at that time. All other galaxies will have receded beyond the cosmological horizon, their light redshifted to immeasurable wavelengths, their presence unknown to any observer who has no access to historical records from an earlier era. This is already happening at the margins, and it is one of the quieter, slower, but deeply significant consequences of living in an accelerating universe. The cosmos is, in a very gradual sense, closing in on itself, not through collapse, but through dispersal. The universe is not coming together. It is spreading apart, and in doing so, it is rendering its own contents invisible to one another, piece by piece, across the deepest stretches of time. There is a particular kind of loneliness embedded in this picture, not a human loneliness, but a cosmic one. A universe that grows not only larger but darker and more isolated as it ages. A cosmos in which the structures we observe today, the rich tapestry of galaxies and galaxy clusters and superclusters that fill the sky with light, will eventually give way to an emptiness so complete that almost nothing remains. That emptiness is where we are headed, and we will begin to trace the path toward it in the next chapter, as we explore the first and most likely of our 3 ending scenarios in detail. Of the 3 possible endings we are exploring tonight, heat death is the most gradual, the most quiet, and the one most directly supported by current observations. It is also, in many ways, the hardest to visualize. The Big Rip and the Big Crunch are endings with a kind of physical drama to them, things tearing apart or everything collapsing inward. Heat death has no such event. There is no singular moment when it occurs. It is not a happening, but a condition, a state the universe slowly approaches over spans of time so vast that no single process, no single change, marks the transition. The universe does not end in heat death, so much as it arrives at a plateau from which no further change is possible. To understand why this is the most probable fate of the universe and what it actually means, we need to engage with one of the most fundamental principles in all of physics, the second law of thermodynamics. The second law states that in any closed system, a system that does not exchange energy with its surroundings, the total entropy of that system will increase over time, or at minimum remain constant. It will never spontaneously decrease. Entropy is a measure of disorder, or more precisely, a measure of the number of microscopic arrangements that are consistent with the macroscopic state of a system. A highly ordered state, one in which all the molecules of a gas are concentrated in one corner of a container, or all the energy in a system is concentrated in a single hot region, corresponds to a relatively small number of possible microscopic arrangements. A disordered state, one in which molecules are spread evenly throughout a container, or energy is distributed uniformly across a system, corresponds to a vastly larger number of possible arrangements. Because disordered states correspond to more possible arrangements, they are statistically far more probable than ordered ones. And because physical processes tend, over time, to move toward more probable states, entropy tends to increase. A hot cup of coffee placed in a cool room will gradually cool down. The heat energy in the coffee will disperse into the surrounding air until the temperature of the coffee and the room reach equilibrium. This process happens spontaneously and irreversibly. The coffee does not spontaneously reheat itself by drawing warmth back from the cooler room. This directional quality of entropy is deeply connected to what we experience as the arrow of time. We perceive time as moving in a particular direction, from past to future, from ordered to disordered, from concentrated to dispersed, precisely because entropy increases in that direction. The second law of thermodynamics is not merely a technical statement about physical systems. It is woven into the structure of our experience. Now consider applying this principle to the universe as a whole. The universe is, to a very good approximation, a closed system. There is no larger environment for it to exchange energy with, and so the second law applies to it. The total entropy of the universe increases over time. Currently, the universe is far from its maximum entropy state. Stars burn brightly, concentrating enormous amounts of energy in small regions of space. Temperature differences exist across the cosmos, between stellar interiors and the cold void of intergalactic space. These temperature differences drive processes: nuclear fusion in stellar cores, chemical reactions on planetary surfaces, and the complex biological machinery of life. All of these processes depend on entropy gradients, on the fact that energy is unevenly distributed, and that physical systems will attempt to even it out. The story of the universe's long-term future, under the heat-death scenario, is essentially the story of entropy winning, of all these gradients gradually flattening out, all these energy differentials slowly equalizing, until nothing remains that can drive any process of any kind. The path toward this state takes an extraordinarily long time, and it proceeds through several distinct phases, each of which represents a different chapter in the cosmos's journey toward equilibrium. In the near term, meaning over the next few billion years, a timescale that is itself almost incomprehensible by human standards, the primary story is that of the stars. New stars will continue to form from the remaining reservoirs of gas in galaxies, though star formation is generally declining across the universe as those reservoirs are gradually depleted. Existing stars will continue to burn through their nuclear fuel, following the life cycle that takes them from main sequence to red giant to white dwarf, or, for the most massive stars, from supergiant to supernova to neutron star or black hole. Our own sun will exhaust its hydrogen fuel in approximately 5 billion years, expanding into a red giant that will likely engulf the inner planets before shedding its outer layers and leaving behind a white dwarf, a dense, Earth-sized ember gradually cooling in the dark. This particular story is worth pausing on, not because it changes the arc of what we are discussing, but because it is a reminder that the heat death of the universe is not an abstract concept. It has local expressions, including one that directly involves our own star. On a much larger scale, in roughly 4 billion years, the Milky Way and the Andromeda Galaxy will collide and merge into a single, larger elliptical galaxy. This collision, despite the dramatic word we use to describe it, will not involve stars crashing into one another. The distances between stars are so vast that the two galaxies will pass through each other largely without individual stellar collisions. What will change is the gravitational structure of the combined system. Clouds of gas will be stirred and compressed, triggering bursts of star formation. Some stars will be flung into intergalactic space. The familiar spiral structure of both galaxies will disappear, replaced by the rounder, smoother shape of an elliptical galaxy. Over many billions of years following this merger, star formation will slow as the remaining gas is used up. The resulting galaxy will become increasingly dominated by aging stars, cooling white dwarfs, and the occasional burst of activity as residual gas clouds collapse to form new stars. Eventually, even this activity will cease. The universe's last stars will not be like our Sun. The final stars to burn will be the smallest, coolest, most fuel-efficient stars, red dwarfs. Red dwarfs are extraordinarily long-lived compared to stars like the Sun. Where the Sun burns its hydrogen over roughly 10 billion years, a small red dwarf can sustain nuclear fusion for trillions of years. The smallest red dwarfs may burn for as long as 10 trillion years, nearly 1,000 times the current age of the universe. But even these patient, long-lived stars will eventually exhaust their fuel. The last red dwarf will flicker out somewhere in the range of 10 trillion years from now, and with it, the stelliferous era will come to a close. The age of stars, the dominant chapter of cosmic history, the era in which light and warmth and the chemistry necessary for life have been available, will end not with any dramatic event, but simply because the fuel has run out. What follows is a universe of remnants, cold white dwarfs slowly radiating away their residual heat, neutron stars spinning in darkness, black holes massive and silent, the gravitational anchors of what were once galaxies, now presiding over a universe in which almost nothing moves or changes on any human-relevant timescale. This is the beginning of the degenerate era, a period that will last far longer than the stelliferous era. Measured in numbers so large, they begin to lose ordinary meaning. During this era, white dwarfs cool toward absolute zero, a process that takes on the order of 10 to the 15th years, a quadrillion years. By the end of this period, the universe is populated primarily by cold, dark stellar remnants and black holes, all very slowly moving apart from one another as the expansion of the universe continues. There is one additional process worth noting during this era, a process so slow it sounds almost fictional, but which arises from straightforward quantum mechanical principles. Protons, the positively charged particles that make up the nuclei of all ordinary matter, may not be perfectly stable over arbitrarily long timescales. Some theoretical models predict that protons decay with a half-life somewhere above 10 to the 34th years. If proton decay occurs on any timescale, then over the immense durations of the degenerate era, all ordinary matter, every white dwarf, every cold planet, every asteroid and comet, would slowly dissolve. The atoms composing them would disintegrate into lighter particles and radiation, leaving nothing behind but a diffuse haze of electrons, positrons, and photons. If protons do not decay, and current experimental evidence has not confirmed any proton decay, only placed lower limits on its half-life, then ordinary matter persists indefinitely into the degenerate era, though in increasingly cold and inert forms. Either way, by the time the black hole era arrives, the universe is a profoundly quiet place. We will continue tracing this path in the next chapter, where we examine the concept of entropy more closely and consider what it means for the universe to approach its final equilibrium state. But for now, let us simply hold the picture of heat death as it is taking shape. Not a catastrophe, but a fading. Not an ending that happens, but an ending that simply, quietly, arrives. Entropy is one of those concepts that sounds technical, but contains within it some of the deepest truths about how the physical world works. We introduced it briefly in the previous chapter as a measure of disorder, of the number of microscopic arrangements consistent with a given macroscopic state. But that definition, while accurate, does not quite capture everything that makes entropy so important. To understand heat death fully, and to understand why the universe has the history it has and the future it does, we need to spend more time with this concept. Let us begin with a simple example that helps build the intuition. Imagine a box divided in half by a partition. On one side of the partition, you place a collection of gas molecules. On the other side, there is nothing, a perfect vacuum. When you remove the partition, the gas expands rapidly to fill the entire box. The molecules spread out, distributing themselves evenly through the available space. This happens spontaneously and quickly, and it happens because the expanded, evenly distributed state corresponds to far more possible microscopic arrangements than the compressed state. With more possible arrangements available, the system naturally moves toward them. Now consider the reverse process. You would never observe all the gas molecules spontaneously gathering themselves back into one half of the box, leaving a vacuum on the other side. Such an event is not impossible in principle. The laws of mechanics do not forbid it, but it is so extraordinarily improbable that it effectively never happens. The number of microscopic arrangements corresponding to the compressed state is so small compared to the number corresponding to the expanded state that the probability of the system spontaneously returning to compression is, for any practical purpose, 0. This asymmetry, the fact that systems naturally evolve toward higher entropy states and do not naturally return to lower entropy states, is the second law of thermodynamics. It is a statistical law, not an absolute one, but in systems containing large numbers of particles, the statistics are so overwhelming that the law holds with essentially perfect reliability. Now extend this thinking to the universe as a whole. The current universe is in a relatively low entropy state, not the lowest possible state, not some perfectly ordered arrangement, but low compared to the maximum entropy state it will eventually reach. The evidence for this is all around us. Stars burn, galaxies rotate, temperature gradients exist across the cosmos. Complexity and structure are widespread. All of this requires entropy gradients, requires the universe to be far from equilibrium. The fact that the universe is currently in this relatively low entropy state is connected, in a deep way, to its origins. The Big Bang established the initial conditions of the universe, and those conditions were characterized by an extremely low entropy state. Not in the sense that matter and energy were smoothly distributed. In fact, the very early universe was remarkably smooth and uniform, which for radiation actually corresponds to low entropy, while the low entropy of gravity relates to that smoothness, providing room for gravitational clumping to occur. The story of cosmic evolution is, in large part, the story of the universe working through its initial low entropy endowment. Gravity takes the initial smooth distribution of matter and amplifies small fluctuations, causing matter to clump into galaxies and stars. Stars concentrate energy and burn it, producing light and heat and heavy elements. Life, where it arises, builds complex structures using energy flows. All of this is the universe increasing its entropy, working through the available gradients, extracting usable energy from ordered states, and converting it into heat. Each step along this path uses up some of the low entropy that was established at the beginning. And each step brings the universe incrementally closer to the maximum entropy state that constitutes heat death. There is a concept in thermodynamics called thermal equilibrium, which is the state a system reaches when all temperature differences have been eliminated, when energy is distributed as evenly as possible given the constraints of the system. A cup of coffee in a room eventually reaches thermal equilibrium with its surroundings. The hot coffee cools, the room warms very slightly, and eventually everything is at the same temperature. At that point, no further spontaneous heat flow is possible. The heat death of the universe is the cosmic equivalent of this thermal equilibrium, a state in which energy is so evenly distributed across the entire universe that no temperature differences remain large enough to drive any process. It is not that the universe becomes cold exactly. It is that temperature differences become negligible. There is no hot place to draw energy from, and no cool place to dump waste heat into. Every engine, every process, every reaction that requires an energy gradient to operate simply stops. This state is sometimes described as maximum entropy, but that phrase requires a small clarification. The maximum entropy of the universe is not a fixed target. It changes as the universe expands. As space grows larger, as more volume becomes available for energy to distribute itself through, the maximum possible entropy of the universe increases. The universe is always chasing a moving target, and the timescale for heat death is determined partly by how quickly the universe expands relative to how quickly physical processes drive entropy toward its current maximum. Under the conditions of an accelerating expansion, the universe expands much faster than physical processes can establish equilibrium across large scales. This means the eventual heat death is not the result of the universe physically reaching thermal equilibrium everywhere simultaneously, but rather of all the processes that require entropy gradients, all the stars, all the chemistry, all the biological and physical complexity, simply running out of the fuel that keeps them going. One of the more philosophically charged aspects of entropy is its relationship to information. In the mid-20th century, the mathematician and engineer Claude Shannon developed a theory of information that revealed a deep mathematical connection between entropy in the thermodynamic sense and entropy in the information theoretic sense. In Shannon's framework, information is associated with the reduction of uncertainty. Knowing the state of a system is equivalent to having low entropy information about it. The connection between these two notions of entropy suggests that the heat death of the universe is not just a physical ending, but an informational one. As entropy increases, information in the classical sense becomes less structured, less organized, less meaningful. The patterns that encode the history of stars and civilizations and living beings gradually dissolve into a uniform background of thermal noise. The universe loses, in some sense, its ability to remember. This is one of the aspects of heat death that physicists and philosophers have found most evocative. Not the cold or the darkness, but the dissolution of distinction. The gradual erasure of the differences that make one thing different from another, one moment different from the next. And yet, from another perspective, this dissolution is simply the completion of a process that has been underway since the beginning. The universe began in a state of extraordinarily low entropy and has been increasing its entropy ever since. Every event in cosmic history, every stellar birth and death, every planetary collision, every chemical reaction, every act of thought in every mind that has ever existed, has contributed in its small way to the entropy budget of the universe. The heat death is not a foreign imposition on the universe. It is the natural conclusion of the same process that has produced everything we see. There is something almost elegant about that, when examined slowly and without resistance. The same tendency that produces stars and planets and life also, inexorably, leads toward the long quiet. The same laws that allow for complexity and experience are the laws that bring them, eventually, to rest. Let us hold that thought for a moment before continuing. We have been tracing the path toward heat death through the concepts of expansion, dark energy, and entropy. In the chapters ahead, we will follow that path more concretely, through the last stars, through the age of black holes, and into the final darkness beyond. But we will also, in due course, turn our attention to the alternative scenarios, the Big Rip and the Big Crunch. Each offers a different trajectory, a different kind of ending, a different answer to the question of how a universe can reach its conclusion. For now, we rest in the framework we have built. The universe is expanding, accelerating, and increasing in entropy. It began in a state of extraordinary order and is working its way with patient and unhurried permanence toward a state of maximum disorder. This is not a tragedy in the scientific sense. It is simply physics. The same physics that made the stars, that made the planets, that made the atoms now resting in your body and moving through your breath. The universe knows, in the only way physics allows for knowing, where it is going, and it has plenty of time to get there. This is a good moment to pause and allow what we have covered so far to settle gently before we continue. We have now established the three main conceptual pillars on which the rest of this journey rests. The first is the expanding universe, the discovery that space itself has been growing since the earliest moments of cosmic history, carrying galaxies apart from one another and cooling the universe as it does so. This expansion is not a force acting on the universe from outside. It is a property of space-time itself, built into the geometry of the cosmos by the conditions of its origin. The second pillar is dark energy, the mysterious component that constitutes the majority of the universe's total energy content and is currently driving an acceleration of that expansion. Dark energy is observed through its effects, but not yet understood at the level of fundamental physics. Its behavior over cosmic time, whether it remains constant, strengthens, or weakens, will determine which of the three possible endings the universe is moving toward. The third pillar is entropy, the principle that physical systems naturally evolve toward states of greater disorder, that energy disperses rather than concentrates, and that the universe as a whole is working through the low entropy endowment it received at its origin. The second law of thermodynamics applies to the cosmos, just as it applies to a cooling cup of coffee, and the ultimate destination it points toward is a condition of maximum entropy, the featureless, eventless equilibrium of heat death. With these three pillars in place, we have been tracing the most probable long-term future of the universe under the heat death scenario. We have seen how the stelliferous era, our current era, the age of stars, will continue for another 100 trillion years as successive generations of stars burn through their nuclear fuel. We have seen how the smallest, most fuel-efficient red dwarf stars will outlast all others, burning faintly for trillions of years before cooling into inert stellar remnants. We have explored entropy not just as a technical concept, but as a deep principle woven into the structure of time itself. The directionality of time, the sense we have that events flow from past to future, that causes precede effects, that broken things do not spontaneously repair themselves, is intimately connected to the increase of entropy. The arrow of time and the arrow of entropy point in the same direction, because they are, in a fundamental sense, the same thing. Now, we are about to continue the journey through cosmic time, following the universe through the degenerate era and into the black hole era, tracking the last significant structures in a cooling and darkening cosmos until we arrive at the threshold of the dark era and the deepest quiet that physics permits. The ideas ahead build naturally on everything we have covered. The patience required to follow them, the willingness to hold very large numbers and very distant futures without rushing through them, is itself a kind of practice, a practice of settling into the scale of things, of allowing the mind to rest in the enormity of the universe without needing to reduce it to something more manageable. Take a slow breath. The universe has been unfolding for nearly 14 billion years, and it will continue for trillions more. There is no hurry. There has never been any hurry. The cosmos proceeds at its own pace, entirely indifferent to urgency, and tonight, so do we. We have been moving through deep time at a measured pace, and now we arrive at one of the most evocative passages in the long story of the universe, the era of the last stars. To appreciate what this era means, it helps to first appreciate what stars mean. Not in the poetic sense, though there is poetry in them, but in the physical sense. Stars are the universe's primary engines of complexity. They are the furnaces in which hydrogen and helium, the simple atoms produced in the Big Bang, are fused into the heavier elements that make up everything we recognize as substantial. Carbon, oxygen, nitrogen, iron, calcium, silicon. All of these were forged inside stars and scattered through space when those stars died. The atoms in your body were, billions of years ago, part of the interior of stars that no longer exist. Stars are also the universe's primary sources of light and heat, at the scales relevant to planetary surfaces and the possibility of life. A planet without a nearby star receives no meaningful energy input, and without energy input, the complex chemical processes that characterize life as we know it cannot be sustained. The warmth you feel, the light that allows you to see, the energy stored in every piece of food, all of it traces back, through a chain of physical processes, to nuclear fusion in the core of our sun. Stars, in other words, are not merely decorative features of the night sky. They are the foundation of complexity in the universe. And so, the era of the last stars is, in a certain sense, the era of the last complexity, the final period in which the physical conditions for the kind of rich, layered existence we know are available. As we noted in the previous chapter, star formation has been declining across the universe for several billion years already. The peak of star formation occurred roughly 10 billion years ago, when galaxies were young and their supplies of cold gas, the raw material from which stars condense, were abundant. Since then, as galaxies have consumed their gas through successive generations of star formation, the rate at which new stars ignite has been gradually falling. This decline will continue. Over the next several trillion years, the remaining gas in galaxies will either be incorporated into stars or dispersed by the energy of stellar winds, supernovae, and the radiation pressure of massive stars. New star formation will become increasingly sporadic, occurring in the isolated pockets of gas that remain, and then ceasing altogether. The stars that will outlast all others are the red dwarfs. These are the smallest and least luminous members of the stellar population. Dim, cool, and extraordinarily fuel efficient. A typical red dwarf has a mass somewhere between about 8% and 50% of the Sun's mass. Because they are less massive, they have less gravitational pressure compressing their cores, and therefore they fuse hydrogen more slowly and at lower temperatures than the Sun does. This reduced rate of fusion comes with a significant advantage in terms of longevity. The Sun will exhaust its core hydrogen in roughly 5 billion years. A red dwarf of about 10% of the Sun's mass can sustain hydrogen fusion for approximately 10 trillion years, nearly 1,000 times longer. The smallest red dwarfs may burn even longer, some theoretical models suggesting lifetimes approaching or exceeding 10 trillion years, depending on how fully they mix their hydrogen from outer layers into their cores. For the next several trillion years, then, the universe will be populated by these patient, dim, long-burning stars. They will not be spectacular objects by the standards of what came before. They emit only a fraction of the light of a star like the sun, burning with a faint red or orange glow that would appear quite dim compared to the stars visible in our night sky today. But they will be burning. They will be fusing. They will be the last sources of steady, nuclear-powered light in the cosmos. During this long era, the universe will look very different from how it appears now. The galaxies that currently populate the sky in their billions, each containing hundreds of billions of stars, will have merged and dispersed and settled into vast, diffuse structures dominated by cold stellar remnants. The brilliant blue and white stars that currently make galaxies like the Milky Way shimmer with light will have been gone for trillions of years. What remains will be scattered red dwarfs, widely separated in the dark, slowly burning. The planets orbiting these red dwarfs, if any remain, having survived the gravitational disturbances of eons of stellar interaction, will receive a dim, reddish warmth. Whether anything lives on such planets, across such timescales, is a question that physics alone cannot answer. It touches on questions about the origin and persistence of life that we understand only imperfectly. But the physical conditions, energy input from a stable star, the presence of liquid water in a suitable temperature range, would not be fundamentally incompatible with life as we know it. There is something both melancholy and quietly beautiful about this picture. A universe that has grown vast and dark and mostly cold, in which the last embers of stellar activity burn in widely scattered points of faint light. These last stars would be, in a certain sense, the final inheritors of the universe's original store of low entropy, the last remaining reservoirs of nuclear fuel that have been patiently waiting since the Big Bang for the gravitational conditions that allow them to ignite. But even patience has its limits. Red dwarfs, for all their longevity, do not burn forever. They too exhaust their hydrogen. Unlike stars like the Sun, which expand dramatically into red giants when their core hydrogen is depleted, red dwarfs are fully convective. Their material circulates throughout the entire star rather than developing a stratified structure. This means they can draw on their entire hydrogen supply over their lifetimes. When the last of that hydrogen is consumed, a red dwarf does not expand. It simply contracts slowly into a white dwarf, a dense, inert sphere of degenerate matter, no longer fusing, slowly radiating away its residual heat. Somewhere around 10 trillion years from now, the last red dwarf will complete this transition. The last nuclear fire in the universe will go out. The stelliferous era will end. This moment, if such a gradual process can be called a moment, is in some ways the most significant transition in the long-term future of the universe. Not because anything catastrophic happens, but because something ends that will never begin again. Star formation will have ceased long before, but as long as the last red dwarfs burn, there is still fusion in the universe. There is still the conversion of hydrogen to helium, still the production of light and heat, and the gentle push of radiation pressure against the surrounding dark. When the last red dwarf goes cold, none of that remains. The universe enters a new phase, the degenerate era, in which the dominant objects are not stars, but their cold, dense remnants. It is a phase defined not by activity, but by the slow, almost geological patience of matter cooling toward absolute zero. and it will last much, much longer than the era of stars it follows. After the last stars have faded, after the white dwarfs have cooled and the neutron stars have slowed their spinning, the universe enters the age of black holes. This era is sometimes called the black hole era, and it is, in terms of sheer duration, one of the longest chapters in the universe's story. It follows the degenerate era, which itself lasted from the end of the stelliferous era, roughly 10 trillion years from now, until the slow dissolution or cooling of the remaining stellar remnants. The black hole era then extends from there across timescales that dwarf even those of the degenerate era by many orders of magnitude. To understand the black hole era, we first need to understand what black holes are in the context of this deep future, and why they are the last significant structures standing when everything else has faded. Black holes form when matter is compressed beyond a critical density, causing space-time to curve so severely that not even light can escape from, within a certain boundary, the event horizon. In the present universe, black holes form primarily through the deaths of massive stars and through the merger of compact objects. Stellar mass black holes range from a few times the mass of the Sun to perhaps 100 solar masses. Supermassive black holes, found at the centers of most large galaxies, range from millions to billions of solar masses. In the far future, after all stars have burned out and stellar remnants have slowly dissipated or merged, black holes are the only objects that retain significant structure. They do not emit light, at least not in any ordinary sense. They do not burn fuel. They do not decay through ordinary chemical or nuclear processes. They simply exist, maintaining their gravitational presence in the darkness, occasionally interacting with whatever sparse matter or other black holes drift close enough. Over the immense timescales of the degenerate era and beyond, black holes will grow through the occasional absorption of whatever matter drifts into their gravitational reach. Cold stellar remnants, rogue planets ejected from their original systems, the diffuse haze of particles that remains after proton decay, if that process occurs. Simultaneously, distant black holes will gradually merge as the galaxies and galaxy clusters that once contained them settle into tighter and tighter configurations under gravity. But even black holes are not permanent. This is the insight that Stephen Hawking contributed to physics in 1974, and it remains one of the most surprising and consequential theoretical results of the 20th century. Hawking showed that black holes are not perfectly black. Through a quantum mechanical process occurring near the event horizon, black holes slowly emit radiation, what is now called Hawking radiation. The mechanism involves the behavior of quantum fields near the event horizon, where the extreme space-time curvature causes effects that result in a very slow but real emission of thermal radiation from the black hole. The key word is very slow. The rate of Hawking radiation is inversely related to the mass of the black hole. Smaller black holes radiate faster. Larger black holes radiate more slowly. For a stellar mass black hole, the rate of Hawking radiation is so infinitesimally small that it is completely negligible compared to the energy the black hole absorbs from the cosmic microwave background radiation that currently pervades the universe. Such a black hole, in the present era, is absorbing far more energy than it emits and is effectively growing. But as the universe expands and cools, the temperature of the cosmic microwave background radiation falls. Eventually, many trillions of years from now, the background radiation temperature will drop below the Hawking temperature of stellar mass black holes, and they will begin to slowly evaporate. For supermassive black holes, which have much lower Hawking temperatures, the evaporation process is correspondingly slower. vastly slower. The timescale for a stellar mass black hole to evaporate via Hawking radiation is approximately 10 to the 67th years. That number requires a moment of reflection. The current age of the universe is approximately 10 to the 10th years. The end of the stelliferous era is roughly 10 to the 13th years from now. The evaporation of a stellar mass black hole takes 10 to the 67th years. We are dealing with a number that is astronomically larger than the already astronomical numbers we have been discussing. For supermassive black holes, the billion solar mass objects at the centers of galaxies, the evaporation timescale is even longer, approximately 10 to the 96th to 10 to the 100th years, depending on their mass. These are the last structures in the universe, the last things that can be said to have a definite location, a definite mass, a definite influence on the space-time around them. During this extraordinarily long era, the universe is a dark and nearly featureless place. Whatever light exists consists of the extremely low-energy photons emitted by cooling black holes through Hawking radiation. Wavelengths stretched by the expansion of the universe to lengths that dwarf any scale we normally work with. The temperature of the universe is a fraction of a degree above absolute zero. Any ordinary matter that survived proton decay exists only as isolated electrons, positrons, and the occasional atom of the lightest elements, drifting through a space so vast and so empty that the probability of any two particles ever encountering each other approaches zero. In this era, time itself takes on a strange quality. Nothing happens, in any ordinary sense, except at the margins of black holes where quantum effects slowly drain them of mass. There are no seasons, no cycles, no events by which an observer, if any could exist, could mark the passage of time. The universe simply is, in the deepest and most featureless sense of that word, for stretches of time that bear no relation to anything in human experience. And then, one by one, the black holes complete their evaporation. Each one, at the end of its long Hawking radiation process, reaches a point where its mass falls below a critical threshold and it releases its remaining energy in a brief burst, a final flash that lasts only an instant on the timescale of black hole evaporation, though it would be energetically significant in the darkness of the late universe. When the last supermassive black hole evaporates, somewhere in the range of 10 to the 100th years from now, the black hole era ends. There are no more significant concentrations of mass or energy anywhere in the observable universe. There are no more structures. There are no more events in any meaningful sense. The universe has arrived at the threshold of the dark era. There is a particular quality of silence that comes with this picture. A silence that is not merely the absence of sound, but the absence of process, of change, of distinction. The universe in the late black hole era is not silent the way a library is silent, or a forest at night. It is silent the way mathematics is silent, a condition in which the question of whether anything is happening has a clear and definitive answer: no. And yet even this silence is not quite the end, because after the black holes are gone, there remains one more passage, the longest and most featureless of all, before the universe reaches the state that truly deserves the name heat death. When the last black hole evaporates, what remains? This is one of the most interesting questions in all of theoretical cosmology, not because the answer is complex, but because it is so strikingly simple. After the last black hole is gone, after the last significant concentration of mass and energy in the universe has dispersed into radiation, what the universe contains is essentially nothing, or as close to nothing as physics permits. there will be photons. The universe will contain a diffuse bath of extremely low-energy photons. The remnants of Hawking radiation from countless black holes, stretched and redshifted by the expansion of the universe over timescales so vast that their wavelengths are longer than anything that has ever existed before. These photons carry almost no energy. They interact with essentially nothing. They simply propagate through the expanding void, growing ever more diffuse and ever lower in energy as the universe continues to expand. There will be electrons and positrons, if proton decay has not occurred. And as we noted, there is currently no confirmed observational evidence that protons decay. Then the universe will also contain a sparse scattering of electrons and their antimatter counterparts, positrons. These particles have no known decay mode in standard physics. They are, to our current understanding, truly stable. Over the vast timescales we are discussing, they will drift through space essentially forever, occasionally coming within quantum mechanical range of each other and annihilating in a brief burst of extremely low-energy radiation. There will be neutrinos. These extraordinarily light, weakly interacting particles were produced in enormous quantities in the early universe and have been streaming through space ever since. Like photons, they carry very little energy in the late universe, having been redshifted by the expansion of space. And that, largely, is it. The universe in the dark era is a near vacuum, populated by a diffuse sea of photons and a sparse scattering of leptons, all separated by distances that are themselves expanding without limit. In this condition, the universe has achieved something very close to thermal equilibrium. The temperature is so close to absolute zero that the distinction between slightly above and at absolute zero is essentially philosophical. There is no physical process that could measure or make use of the difference. The distribution of energy is so uniform and so diffuse that no gradient exists along which any process could run. This is heat death, not a moment of catastrophic finality, but a condition, a state of the universe in which the second law of thermodynamics has done all the work it can do, and nothing more is possible. It is worth sitting with what maximum entropy actually feels like as a description of a physical state. In the everyday world, when we say a room is in a state of maximum entropy, maximum disorder, we usually mean something like clutter, randomness, chaos. But the maximum entropy state of the universe is, in a strange sense, the opposite of chaotic in the colloquial meaning of that word. It is uniform, featureless, perfectly smooth. Chaos, in the everyday sense, involves complexity, many different things happening at once, interacting in unpredictable ways. Maximum entropy, in the thermodynamic sense, involves the complete absence of that kind of complexity. There is nothing to interact, nothing to vary, nothing to generate any kind of event. It is not chaos. It is the deepest possible stillness. Some physicists and philosophers have asked whether this state is truly permanent, whether the universe, once it reaches maximum entropy, remains there forever. The answer, under standard physics, is essentially yes, with one extremely important qualification. The qualification involves fluctuations. Even in a universe at maximum entropy, quantum mechanical and thermal fluctuations will continue to occur. On extraordinarily rare occasions, random fluctuations in the quantum fields that pervade space could, in principle, produce spontaneous, localized decreases in entropy. Small, transient pockets of order arising from the background of maximum disorder. This possibility was discussed by Ludwig Boltzmann in the 19th century, and it remains a topic of genuine interest in theoretical physics. The most famous version of this idea involves what is called a Boltzmann brane, a hypothetical scenario in which a random thermal fluctuation produces, by pure chance, a fully formed conscious mind complete with memories and sensory experiences, arising spontaneously from the thermal background. Such an event is not forbidden by physics. It is simply extraordinarily improbable. So improbable that the expected waiting time for a single such fluctuation to occur is itself measured in numbers that make even the black hole evaporation timescales look brief. The Boltzmann brane concept is less a practical prediction and more a thought experiment about the nature of probability and the relationship between randomness and experience. It highlights the fact that in a universe of infinite time and non-zero quantum fluctuations, almost anything that is not physically forbidden will eventually occur, but with waiting time so vast that the word eventually loses any ordinary meaning. A more physically grounded version of fluctuation-based processes in the late universe involves the possibility that rare quantum fluctuations could, over timescales of 10 to the 10 to the 10th years or more, produce something like a new Big Bang, a spontaneous fluctuation large enough to seed a new cosmological expansion. This idea is speculative and depends on assumptions about the quantum gravitational behavior of the universe that we do not currently have a complete theory to describe. But it gestures toward the possibility that the heat death of our universe might not be the last word, that the same quantum uncertainty that gives rise to particles and processes at small scales might, given enough time, give rise to something much larger. We hold that possibility lightly, as the speculative but genuinely interesting idea it is. What we can say more confidently is this: in the dark era, in the long stillness after the last black hole has evaporated, the universe has reached a condition that represents, for all practical purposes, the end of the story under the heat death scenario. Not the end of time itself, if time continues to flow in the absence of any processes to mark it. Not the end of space, which continues to expand, but the end of change, the end of complexity, the end of any process that could be called an event. Everything that ever existed, every star, every galaxy, every planet, every living thing, every thought and action and artifact of every civilization that ever arose, will have long since dissolved back into the background. The universe will have no memory of any of it, except in the purely physical sense that the distribution of matter and energy in the very late universe was shaped, in ways too diffuse to trace, by everything that came before. The universe will be old beyond any measure that feels meaningful, and it will be quiet in a way that words were not really designed to describe. This is where the heat death scenario leads us, not to a bang or a rip, but to a long, slow, utterly complete dissolution of everything that distinguished one moment from the next. Let us rest here for a while before we turn to the alternative scenarios, to the Big Rip and the Big Crunch, which offer different paths, different timescales, and different answers to the question of how a universe can end. The next chapters will carry us in a different direction entirely, not forward through the slow cooling of an aging cosmos, but into the more dramatic possibilities that arise if dark energy behaves differently than we currently believe, or if the expansion of the universe should, against present expectations, one day reverse. Before we turn to the alternative endings, to the Big Rip and the Big Crunch, this is a natural moment to pause and let the ground we have already covered settle. We have been moving through an enormous amount of conceptual territory, and the ideas we have explored deserve a moment of quiet consolidation before we continue. We began by establishing a framework for thinking about cosmic time, a way of holding durations so vast they resist ordinary imagination, we introduced the concept of deep time, the recognition that immense temporal scales have structure and texture, that events unfold and processes complete themselves across billions and trillions of years, and that the laws of physics allow us to reason about those events even when no observer will ever witness them directly. We placed our current moment in context. The universe is roughly 13.8 billion years old. We live during the stelliferous era, the age of stars, which began about 100 million years after the Big Bang and is expected to continue for another 100 trillion years. By the standards of the universe's own timeline, we are near the beginning. The most fuel-efficient stars have barely begun their multi-trillion-year lives. The age of stellar light and warmth has most of its duration still ahead. We trace the discovery of cosmic expansion and the role that dark energy plays in determining how that expansion evolves. We examine the equation of state parameter that characterizes dark energy's behavior, and we understood why the precise value of that parameter determines which of the three possible endings the universe is heading toward. We noted that current measurements place dark energy closest to a stable cosmological constant, pointing toward heat death as the most probable outcome, while acknowledging that the uncertainties in those measurements leave room for other possibilities. We then followed the heat death scenario in considerable detail. Through the long era of stellar burning, through the quiet centuries and millennia of stellar remnant cooling, through the extraordinary timescales of black hole evaporation, and into the dark era, the vast, cold, featureless expanse of maximum entropy that represents the furthest destination of the heat death path. Along the way, we engage deeply with entropy, with the second law of thermodynamics as a principle that applies not just to cups of coffee in cool rooms, but to the universe as a whole. We understood entropy not merely as a measure of disorder, but as a directional tendency in the behavior of physical systems, a tendency that gives the universe its arrow of time and eventually brings it, after unimaginable stretches of process and change, to a condition of perfect, uniform, eventless equilibrium. We noted the connection between thermodynamic entropy and information. The insight, developed by Claude Shannon in the mid-20th century, that the two concepts share a deep mathematical relationship. As the universe moves toward maximum entropy, it moves also toward minimum information, a condition in which the distinctions that allow meaning to exist have been erased. The patterns that encode history have dissolved, and the universe retains no readable record of the complexity it once contained. We have also, throughout this journey, spent time with the human dimension of these questions, with what it means to exist in a universe whose ending, however distant, is written into its physical properties. We have reflected on the shift in perspective that cosmic thinking offers, the way deep time loosens the grip of everyday urgency, and the way the finitude of the universe's active era makes the present moment of that era, our moment, feel both very small and strangely precious. All of that forms the foundation on which the next section of our journey rests. We are now going to turn away from the most probable ending and consider the alternatives, the scenarios that require conditions different from what we currently observe, but that cannot be ruled out, and that illuminate different aspects of what the universe is and what it might become. The Big Rip and the Big Crunch are not merely curiosities. They are genuine possibilities, each grounded in real physics, each telling us something important about the nature of dark energy and the structure of space-time. Understanding them fully requires everything we have already built: the framework of expansion, the role of dark energy, the principle of entropy. brought to bear on scenarios that push those concepts in new directions. So let us continue. The universe has more to show us, and we have the time to look carefully. Until now, we have been tracing the most probable fate of the universe, the long, slow cooling that leads toward heat death. But probability is not certainty, and the universe has not yet revealed, with complete precision, what dark energy will do over the vast timescales ahead. If dark energy is not a cosmological constant, if it is instead a dynamic field whose energy density increases over time, then the universe's future looks very different from the quiet dissolution we have been describing. Under these conditions, the expansion of space does not merely continue at a steady accelerating rate. It accelerates more and more with each passing moment, growing stronger and stronger, until the force driving expansion overwhelms every other force in nature, tearing the universe apart on progressively smaller scales. This is the Big Rip. The term was introduced by the cosmologist Robert Caldwell and his colleagues in a 2003 paper that outlined the mathematical conditions under which this fate would occur. The key ingredient is what Caldwell called phantom energy, a form of dark energy with an equation of state parameter less than -1, meaning the energy density of dark energy actually increases as the universe expands, rather than remaining constant or decreasing. Under phantom energy conditions, the expansion of the universe does not just accelerate, it superaccelerates. The rate of expansion grows without bound, approaching infinity in a finite amount of time. This produces what mathematicians call a finite time singularity, a point in the future at which the expansion rate becomes infinite. Everything that exists is torn apart before that point is reached, because the accelerating expansion overwhelms the forces holding structures together. The Big Rip unfolds in a sequence, working from the largest scales down to the smallest. Understanding this sequence helps to make the scenario concrete, even if the physics behind it remains speculative. The first structures to come apart are the largest. Galaxy clusters, the gravitational associations of hundreds or thousands of galaxies that represent the largest bound structures in the present universe, are held together by gravity acting across tens of millions of light years. As the expansion of the universe accelerates under phantom energy conditions, the force driving expansion grows large enough to overcome the gravitational binding of these clusters. Galaxies that have been gravitationally associated for billions of years begin to drift apart, pulled by the accelerating fabric of space. This process begins slowly. In the early phases of phantom energy domination, the effect is subtle. A slight increase in the recession velocities of distant cluster members, a gradual loosening of the gravitational web. But phantom energy grows stronger over time, and the loosening becomes faster. Depending on the specific value of W and the current density of dark energy, the Big Rip might occur anywhere from tens of billions of years in the future to much longer timescales. Some models place it as close as 20 billion years from now, not enormously longer than the current age of the universe. Others place it much further out. The uncertainty in current measurements of W means we cannot say precisely when, if ever, this scenario plays out. But working from a representative model, let us trace the sequence of events in the final phases before the Big Rip. Roughly a billion years before the Rip, galaxy clusters have fully dispersed. Individual galaxies drift in isolation, their member stars no longer gravitationally associated with the larger clusters they once belonged to. The universe at this stage looks dramatically different from today. Not a tapestry of interconnected structures, but a scattered field of isolated galaxies, each receding from all others at increasing speed. Approximately 100 million years before the rip, individual galaxies begin to feel the strain. The dark energy driving expansion has grown strong enough to pull at the gravitational binding of galaxies themselves. Stars that have orbited galactic centers for billions of years find their orbital paths disrupted. The outer regions of galaxies begin to fray, stars drifting away into the expanding void. Over the following millions of years, galaxies dissolve entirely, not through any collision or explosion, but simply through the relentless stretching of space between their member stars. About a year before the rip, measured in ordinary years, which is a vanishingly small interval on the timescales we have been discussing, solar systems face the same fate as galaxies. The expansion of space has grown strong enough to overcome the gravitational binding of a star and its orbiting planets. Planets spiral outward, released from the gravitational grasp that has kept them in stable orbits. A star that has held its planets for billions of years loses them in a matter of months as the expansion rate reaches this threshold. In the final hours before the rip, the expansion of space overcomes the electromagnetic forces holding atoms and molecules together. Planets, which have already lost their orbital companions, now begin to come apart themselves, their rocky surfaces and metallic interiors disaggregating as the bonds between atoms weaken and then fail. What was solid becomes, in those final hours, a rapidly dispersing cloud of particles. In the final fraction of a second, the expansion overcomes even the strong nuclear force, the force that holds protons and neutrons together within atomic nuclei. Nuclei are torn apart. Protons and neutrons are separated. And then, in what some theoretical treatments suggest is the true final moment, even the quarks within protons and neutrons are pulled apart, if the energy scale of the rip is sufficient. At the moment of the Big Rip itself, the instant when expansion becomes formally infinite, space-time itself reaches a singularity. Every point in space is torn from every other point. The metric of space-time breaks down. Physics, as we currently understand it, cannot describe what happens at or after this moment, because our theories are not equipped to handle the conditions of an infinite expansion rate. The Big Rip is, in this sense, a genuine ending, not a gradual cooling, but a sudden, absolute termination. It is not violent in the way a human experience of violence is. There is no shock wave, no sound, no impact. It is a structural failure of space-time at the most fundamental level. The universe does not blow up. It simply comes apart, at every scale simultaneously, in the final moments of an acceleration that has been building for billions of years. There is something that feels almost paradoxical about the Big Rip compared to heat death. Heat death arrives after an incomprehensibly long stretch of time. The universe, growing older and colder and darker for durations that make the current age of the universe seem like an opening note. The Big Rip, depending on the model, could arrive relatively soon, within tens of billions of years, or at most, a few 100 billion. It is the shorter, sharper ending, the one that cuts across the long arc of the heat-death scenario with an abrupt structural failure. Whether it will occur depends entirely on whether dark energy strengthens over time. Current observations constrain W to values very close to -1, which is more consistent with a stable cosmological constant than with phantom energy. But the measurement uncertainties allow for phantom energy scenarios, and until those uncertainties are reduced, the Big Rip remains a genuine possibility among the set of futures consistent with what we observe. It is also worth noting that the Big Rip, for all its structural drama, would not be experienced by any observer, in the way its description might suggest. The sequence of events, from galaxy cluster dispersal to nuclear disintegration, unfolds on timescales ranging from billions of years to fractions of a second. Any civilization or life form existing in such a universe would have eons of warning, but no ability to prevent what the expansion of space was doing on the largest scales. And the final moments, the tearing of atoms and nuclei, would occur so quickly that no physical process involving information or experience could register them. The Big Rip is not something that happens to observers. It is something that happens to the universe itself, at every scale, in a cascade that concludes with the dissolution of the conditions that make observation possible. If the Big Rip represents an ending driven by expansion growing too strong, the Big Crunch represents its mirror image, an ending driven by expansion failing, slowing, stopping, and ultimately reversing. The Big Crunch was, for much of the 20th century, considered the most scientifically plausible of the three ending scenarios. Before the discovery of cosmic acceleration in 1998, many cosmologists believed the universe contained enough matter to eventually halt its expansion. The gravitational pull of all the matter in the universe, acting across cosmic scales, seemed like a natural counterweight to the momentum of the Big Bang. Given enough time, the thinking went, gravity would win. The discovery of dark energy and the accelerating expansion significantly reduced the probability of the Big Crunch under standard cosmological models. If dark energy is a stable cosmological constant, there is no mechanism by which the expansion can reverse. The repulsive effect of dark energy grows as the universe expands, permanently overwhelming gravity on large scales. A Big Crunch requires either an absence of dark energy or a form of dark energy that weakens and eventually disappears over time. Neither of these conditions appears to be favored by current data, but neither can be definitively ruled out, and so the Big Crunch remains a legitimate scenario worth understanding in detail. Let us trace how it would unfold, assuming the conditions that make it possible. The first sign of a Big Crunch universe would be a change in the redshift of distant galaxies. In the current universe, distant galaxies are redshifted. Their light is stretched to longer wavelengths by the expansion of space. In a universe where expansion has slowed and begun to reverse, distant galaxies would eventually show blue shift instead. Their light compressed to shorter wavelengths as the space between us and them begins to contract. This transition from redshift to blue shift would not happen suddenly. It would be a gradual change in the pattern of observed spectra, detectable first in the most distant galaxies whose light has been traveling for the longest time. Astronomers, if any existed in such a universe, would notice over centuries and millennia that the most distant objects were no longer receding as fast as models predicted, and eventually that they were beginning to approach. The contraction of the universe would begin slowly, for the same reason that the original expansion was slow in its early phases. The reversal of expansion is, mathematically, the time reverse of expansion. It starts gently and accelerates as matter comes closer together and gravitational attraction grows stronger. Over billions of years, the structure of the universe would change in ways that are, in some respects, the reverse of its historical development. Galaxies that have been drifting apart for billions of years would begin to drift back together. The large-scale cosmic web, the network of filaments, walls, and voids that constitutes the large-scale structure of the observable universe, would begin to compress. Voids would shrink. Filaments would thicken. Galaxy clusters would draw their members closer. This process would not be perfectly symmetric with the expansion phase, because the universe at the beginning of contraction would be very different from the universe at the beginning of expansion. The universe currently contains stars, planets, black holes, and complex chemical structures that did not exist in the early universe. The collapse would therefore proceed through a cosmos that is, in its local structures, far more complex than the smooth early universe was. As the contraction continues, the distance between galaxies shrinks. The temperature of the universe begins to rise because the cosmic microwave background radiation, the diffuse sea of photons that fills the universe, is blue shifted by the contraction just as it was redshifted by the expansion. The photon temperature, which has been falling for the entire history of the expanding universe, begins to climb. In the later stages of contraction, the universe grows hot enough that the radiation background begins to affect the structures within it. Stars, which have been radiating heat into a cold void for their entire lives, find themselves surrounded by a background radiation that is growing warmer. Eventually, the background temperature rises above the surface temperature of stars, at which point the entire universe is hotter than a stellar surface. Stars no longer radiate effectively. They are embedded in a radiation field as hot as or hotter than themselves. The galaxies that have spent billions of years as well-separated islands of stars and gas are now packed into a shrinking space, colliding and merging with increasing frequency. The distinction between one galaxy and another dissolves. Matter that was organized into stars and planets, and the vast emptiness between them, is compressed back into a denser and denser state. Black holes, which in the heat-death scenario are the last surviving structures, play a different role in the Big Crunch. As the universe contracts, black holes merge with increasing frequency. The enormous supermassive black holes at galactic centers, already billions of solar masses, grow larger as they absorb the matter falling inward from the collapsing universe. But even these giants are ultimately overwhelmed by the surrounding density as contraction approaches its end. In the final moments of the Big Crunch, the universe approaches a state of density and temperature comparable to those of the very early universe. All structure has been erased. Matter and radiation have been compressed into a hot, dense, uniform plasma. The distinction between individual particles becomes meaningless as the density approaches values where our current physics breaks down. The final singularity, if a singularity is indeed what the mathematics implies, is the endpoint of this compression, a state of infinite density and temperature, a point beyond which the equations of general relativity cannot reach. In some ways, it is the mirror image of the Big Bang, a final crunch that brings everything to an end in conditions of extraordinary intensity. What happens at or beyond this singularity is, again, beyond the reach of current physics. General relativity, which describes the large-scale structure of space-time, breaks down at singularities. A complete theory of quantum gravity, one that successfully unifies the principles of general relativity with those of quantum mechanics, would be required to describe the physics of the final crunch. We do not yet have such a theory, though several promising frameworks are being actively developed. One of the most intriguing questions raised by the Big Crunch is what it implies for time. If the universe contracts to a singularity, does time end at that singularity, just as it began at the Big Bang singularity? Or does time continue in some form beyond the crunch, perhaps feeding into a new phase of expansion? This question leads us naturally into the next chapter, where we explore the possibility of a universe that does not truly end but instead cycles, collapsing and re-expanding, perhaps infinitely. But before we move there, it is worth pausing to consider the Big Crunch. from a perspective that is easy to overlook in the technical details. The Big Crunch is, among the three scenarios, the one that most directly mirrors the universe's origin. The Big Bang and the Big Crunch bracket the universe's history, one at each end, in a kind of cosmic symmetry. The universe emerges from a point of extreme density and returns to one. Whether this symmetry is truly there, or whether it is an artifact of models that may not capture the full complexity of what would actually occur, is a question that remains open. But the image of a universe that begins and ends in the same kind of extraordinary condition carries a certain completeness, a sense of the universe as a bounded thing with a beginning and an end, a story with both an opening and a closing line. The Big Crunch, as we described it in the previous chapter, raises a question that has occupied cosmologists and philosophers for decades. If the universe collapses to a singularity, does everything simply end? Or does the collapse seed something new? A new expansion, a new universe, a new chapter in a story with no beginning and no end? This question is the starting point for what are collectively called cyclic cosmologies, theoretical frameworks in which the universe undergoes repeated cycles of expansion and contraction, or in which the ending of one phase of cosmic evolution gives rise to the beginning of another. The simplest version of this idea is the Big Bounce. In a Big Bounce cosmology, the contracting universe does not reach a true mathematical singularity, a point of infinite density, but instead reaches a very high but finite density at which quantum gravitational effects become significant. At this point, the collapse is halted and reversed by quantum pressure, similar to the way that quantum mechanical effects prevent a neutron star from collapsing into a black hole at nuclear densities. The universe bounces, beginning a new phase of expansion. If this were the case, our Big Bang, the beginning of our current phase of cosmic expansion, would not have been the absolute origin of time and existence. It would instead have been a bounce point, the moment of minimum size in an oscillating universe that had existed, in some form, for arbitrarily long before our current expansion began, and would continue for arbitrarily long after our current expansion ends. The appeal of the Big Bounce idea is partly philosophical. An oscillating universe with no true beginning and no true ending avoids what many physicists find troubling about cosmological singularities, the breakdown of physical law at a point where our equations lose their meaning. If the universe never truly reaches a singularity, the laws of physics remain valid throughout, and the question of what happened before the Big Bang has a straightforward answer: a previous phase of cosmic evolution. However, the original versions of the oscillating universe model ran into a serious obstacle related to entropy. Recall that the second law of thermodynamics requires the entropy of a closed system to increase over time. If the universe oscillates through repeated cycles of expansion and contraction, each cycle must have higher entropy than the previous one, because entropy cannot spontaneously decrease. This means successive cycles must be longer and larger than their predecessors. The universe must grow with each bounce, rather than repeating the same cycle indefinitely. Working backward from this constraint, one arrives at an uncomfortable conclusion. If entropy must increase with each cycle, then very early cycles had very low entropy, but an infinite sequence of previous cycles would have required the universe to have started with zero or negative entropy at some arbitrarily remote point in the past, which is physically undefined. The entropy argument therefore suggests that even a bouncing universe must have had a beginning, a first cycle, which does not fully solve the problem of origins that the cyclic idea was designed to address. More sophisticated cyclic models have been developed that attempt to address this entropy problem in various ways. The ekpyrotic model, developed by Paul Steinhardt and Neil Turok in the early 2000s, draws on ideas from string theory and proposes that our universe is a higher dimensional membrane, or brane, that periodically collides with an adjacent brane in a higher dimensional space. Each collision produces a new Big Bang, and the entropy of the colliding system is reset in each collision through a process that distributes entropy across the larger, higher dimensional space. The ekpyrotic model is technically sophisticated and remains an active area of theoretical research. It makes predictions that, in principle, could be tested by observations of the cosmic microwave background, specifically through patterns in the polarization of that radiation that would distinguish ekpyrotic bounces from standard inflationary Big Bang models. So far, observational data has not confirmed or ruled out the ekpyrotic model with certainty. Another cyclic framework comes from loop quantum cosmology, a quantization of general relativity that replaces the smooth spacetime of classical physics with a discrete granular structure at the smallest scales. In loop quantum cosmology, the extreme density at the end of a contracting universe creates quantum geometric effects that generate a repulsive force, preventing the formation of a true singularity and causing the universe to bounce into a new expansion phase. This framework has been developed extensively by Abhay Ashtakar and colleagues, and it provides a mathematically consistent description of a bouncing universe that avoids the singularity problem. Cyclic cosmologies of various kinds share a common thread. They transform the question of the universe's ending into a question about transition. The end of one cycle is the beginning of the next. The Big Crunch, in this framework, is not a termination, but a threshold, a passage from one phase of cosmic existence to another. This idea resonates with certain intuitions that many people carry about the nature of endings and beginnings. In human experience, many apparent endings turn out to be transitions. The end of one season is the beginning of the next. The end of one phase of life opens into another. The cyclic universe takes this intuition and writes it into the laws of physics themselves, proposing that even the most total of cosmic endings is, in some deeper sense, a beginning. Whether this is actually true of our universe depends on physics we do not yet fully understand, specifically the behavior of spacetime at the extreme densities associated with the bounce point. A complete theory of quantum gravity would be required to determine whether a true singularity forms at the end of a Big Crunch universe, or whether quantum effects intervene to produce a bounce. Until that theory exists, cyclic cosmologies remain well-motivated theoretical possibilities rather than confirmed descriptions of reality. It is worth noting that the cyclic universe idea, in various forms, has a very long intellectual history. Cultures around the world have independently developed cosmological frameworks in which time is cyclical rather than linear, in which the universe repeats itself, either exactly or with variations, through endless cycles of creation and dissolution. Hindu cosmology, for instance, describes vast cycles of time called kalpas, each lasting billions of years, during which the universe is created and dissolved by Brahma. Ancient Greek Stoic philosophers proposed a doctrine of eternal recurrence, in which the universe periodically destroys itself in a great conflagration and is reborn in exactly the same form, repeating the same events in the same order throughout infinite time. These ancient frameworks were not scientific theories in the modern sense. They lacked the mathematical precision and observational grounding of contemporary cosmology. but they were engaging with the same fundamental questions about whether time has limits, about whether endings are real or illusory, about the relationship between the universe's beginning and its end. And in their own ways, they arrived at answers that rhyme, at least loosely, with some of what modern physics is now exploring. The universe we live in may or may not be cyclic. It may be heading toward heat death, toward a big rip, toward a big crunch, or toward a bounce that initiates a new phase of expansion. We do not yet know with certainty. What we do know is that the question is genuine, that it is amenable to investigation through physics and mathematics, and that the answer, when we eventually have one, will be one of the most significant things humanity has ever learned. We will continue now with the next chapter, where we explore the boundaries of what physics can and cannot tell us about these possible futures, and what it means to ask questions that currently lie beyond the reach of our best theories. Throughout this journey, we have been following the thread of what physics knows or believes with varying degrees of confidence about the long-term future of the universe. We have explored the mechanics of expansion, the nature of dark energy, the slow progression of entropy, the timescales of stellar death, and the theoretical frameworks of the Big Rip, the Big Crunch, and Cyclic cosmologies. But it is equally important, perhaps more important in a certain sense, to be honest about where that thread runs out, because there are places in this territory where our current understanding genuinely ends, where the questions we are asking push beyond the boundaries of what existing physics can reliably address. This is not a failure of science. It is a description of science as it actually exists, a living, evolving enterprise that is perpetually working at its own edges, extending its reach into territory it has not yet fully mapped. The frontier is real, and it is worth understanding where it lies. One of the most significant gaps in our understanding involves the nature of dark energy itself. We have discussed dark energy extensively throughout this script, noting that it constitutes roughly 68% of the universe's total energy content and drives the accelerating expansion we observe. But we have also noted repeatedly that we do not know what dark energy actually is. This uncertainty is not a minor technical detail. It is the central unknown in cosmology, and it directly determines which of our three ending scenarios will come to pass. If dark energy is a cosmological constant, heat death is the most likely outcome. If it is phantom energy, the Big Rip awaits. If it weakens sufficiently over time, the Big Crunch becomes possible. The entire question of how the universe ends hinges on a property of the universe that we currently cannot explain from first principles. Our best theoretical frameworks do not yet provide a satisfying account of why the cosmological constant has the value it does. Quantum field theory, as we discussed earlier, predicts a vacuum energy density many orders of magnitude larger than what is observed, explaining why the observed value is so much smaller than the predicted value. The cosmological constant problem remains one of the most vexing open questions in theoretical physics. Without understanding why dark energy has its current value, we have no reliable basis for predicting how it will evolve, or whether it will evolve at all. This situation is intellectually uncomfortable, but scientifically productive. The gap in our understanding motivates the development of new theoretical ideas and new observational programs. Several major observational missions currently operating or soon to begin, including the Euclid Telescope, the Dark Energy Spectroscopic Instrument, and the Nancy Grace Roman Space Telescope, are designed specifically to measure dark energy properties with unprecedented precision. The data they produce over the coming decades will constrain W more tightly, reduce the uncertainty about dark energy's behavior, and potentially distinguish between some of the theoretical models currently on the table. But even with better data, there may be aspects of dark energy that remain beyond observational reach, at least with technologies available in the near future. The behavior of dark energy at the very early universe, for instance, during the first fractions of a second after the Big Bang, is difficult to probe directly, and the behavior of dark energy in the very far future, tens of billions of years from now, cannot be directly observed from our current position in cosmic time. We must always extrapolate, always extend our models beyond the range of our measurements, and that extrapolation carries with it genuine uncertainty. A second major area of uncertainty involves the quantum nature of gravity. We have a highly successful theory of gravity, Einstein's general relativity, and we have a highly successful framework for describing subatomic physics, quantum field theory. But these two frameworks are fundamentally incompatible with each other at the mathematical level. They are built on different foundational assumptions, use different mathematical structures, and make predictions that disagree in regimes where both are expected to apply simultaneously. Specifically, at extremely high densities and temperatures, such as those near the Big Bang singularity or a Big Crunch singularity. Developing a theory of quantum gravity that successfully unifies these two frameworks is one of the great outstanding problems of theoretical physics. Several approaches are being actively pursued. String theory proposes that the fundamental constituents of nature are not point particles, but tiny, vibrating strings of energy, and that the geometry of the extra spatial dimensions in which these strings vibrate gives rise to the particles and forces we observe. Loop quantum cosmology, as mentioned earlier, quantizes the structure of spacetime itself, treating space as made up of discrete quantum units, rather than a smooth continuum. Various other approaches, causal dynamical triangulations, asymptotic safety, causal set theory, offer different mathematical routes toward the same goal. Each of these frameworks makes somewhat different predictions about what happens at the extreme conditions associated with cosmological singularities. Some predict that singularities are avoided through quantum effects, leading to bounce scenarios. Others maintain singularity formation, but modify the physics in ways that change the character of the endpoint. Until we have a confirmed, empirically validated theory of quantum gravity, we cannot say with confidence what happens at the end of a collapsing universe, or what preceded the Big Bang. This uncertainty extends to the very concept of time. General relativity treats time as a dimension of a four-dimensional space-time manifold, a continuous, smooth background against which events occur. Quantum mechanics treats time as an external parameter, a fixed backdrop against which quantum states evolve. In a theory of quantum gravity, the nature of time itself may need to be reconsidered. Some approaches suggest that time is emergent, that it arises from quantum correlations between subsystems of the universe, rather than being a fundamental feature of the underlying physics. If time is emergent, then questions like what happens after the Big Crunch, or what came before the Big Bang, may not have well-posed answers in the ordinary sense. The question assumes the existence of a temporal framework outside the universe, which may not exist. These are genuinely deep conceptual issues that physics has not yet resolved. There is also the question of what happens to information in the very long-term future of the universe. In classical physics, information is conserved. The state of a physical system at one time determines its state at all other times, in principle. But in quantum mechanics combined with general relativity, this principle runs into difficulties, particularly in connection with black holes. Hawking's original calculation of black hole radiation suggested that the radiation emitted by an evaporating black hole was purely thermal, that it carried no information about what had fallen into the black hole. If true, this would mean that black hole evaporation destroys information, violating a fundamental principle of quantum mechanics. This apparent paradox, the black hole information paradox, has been a central puzzle in theoretical physics for decades. More recent work, particularly drawing on insights from the ADS/CFT correspondence in string theory and the study of entanglement entropy, suggests that information is in fact preserved during black hole evaporation, that it is encoded in subtle correlations in the Hawking radiation, even if it is practically impossible to decode. But a complete, rigorous resolution of the information paradox remains an active area of research, and its full implications for the very long-term future of the universe have not been completely worked out. If information is preserved, then in principle, the state of the late universe, after all black holes have evaporated and the universe has reached something like the dark era, carries, encoded in its photon distribution and quantum fields, a complete record of everything that ever happened. Not a readable record, not one that any conceivable physical system could decode, but a record in the mathematical sense, a state of the universe uniquely connected by the laws of physics to all the states that preceded it. This idea that the universe's entire history is somehow encoded in its final state is philosophically striking, even if it has no practical consequences. It suggests that nothing is truly lost in the strictest physical sense, that the stars and planets and lives and events of the universe's active era leave traces, however unreadable, in the quiet state that follows. Whether this is comforting or merely interesting depends on the perspective one brings to it. As a physical fact, it is simply a consequence of unitarity, the principle that quantum mechanical evolution preserves information. As a philosophical observation, it invites reflection on what it means for something to persist, whether a mathematical encoding in a cold, diffuse quantum state constitutes any meaningful form of memory or continuity. We cannot answer these questions fully here, because physics itself has not yet answered them. What we can do is acknowledge them honestly, recognize that our understanding, thorough as it is in many respects, has genuine limits, and that those limits are not embarrassments but invitations. Invitations to continue developing the theoretical frameworks, continue making the observations, continue asking the questions that might, over decades and centuries of scientific work, extend the reach of human understanding further into the territory that currently lies beyond it. The universe has been generous with its secrets so far. There is reason to hope it will continue to be. One final area of uncertainty worth mentioning is the possibility that our universe is not the only one, that it exists within a larger structure, sometimes called the multiverse, in which many universes with different physical properties exist simultaneously or sequentially. Multiverse ideas arise naturally in several theoretical contexts, including eternal inflation, string theory's landscape of possible vacuum states, and the many worlds interpretation of quantum mechanics. If a multiverse exists, then the fate of our universe is just one story among an incomprehensibly large number of stories. Other universes may be heading toward different endings, governed by different values of dark energy, different physical constants, different initial conditions. In some of those universes, perhaps, conditions amenable to life persist for much longer than in ours. In others, the expansion rate or the strength of gravity might be different in ways that lead to immediate collapse or runaway expansion before any structure can form. The multiverse idea is deeply speculative. It is difficult to test observationally because by definition other universes lie beyond our cosmological horizon. But it represents a genuine possibility that some of the most respected theoretical physicists take seriously, and it provides important context for thinking about the fate of our particular universe. If there are many universes, the specific ending of ours is not the ending of everything. It is one conclusion among many, in a structure larger than any single cosmological story. That is a thought worth carrying, gently, without either dismissing it or leaning on it too heavily. The physics that supports multiverse ideas is real, even if the multiverse itself is not yet confirmed, and the possibility that our universe is nested within something larger than itself, that the story continues beyond any ending we can currently imagine, is consistent with everything we know, even if it goes beyond what we can directly observe. Physics stands, on these questions, at an honest frontier. What lies beyond it is not emptiness, but possibility. The possibility that future generations, equipped with better theories and better instruments, will be able to extend the map further and perhaps arrive at answers that would surprise us. We have spent a long time tonight in the company of very large numbers and very distant futures. We have traced the expansion of the universe across billions and trillions of years, followed the last stars as they cool and dim, watched black holes evaporate over timescales that make the word immense seem inadequate. We have considered what it means for everything to end, not in the abstract, but in the specific, physical, detailed sense that cosmology makes possible. And now, before we close, it is worth turning that immense perspective back toward the human scale, toward the question of what any of this means for us, living as we do in a brief flicker of time near the beginning of the universe's history, on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies. This is not a digression from the science. It is, in a sense, the science completing itself, because the point of understanding the universe is not merely to accumulate facts about it, but to integrate those facts into a richer, more honest, more fully informed way of being in the world. The first thing that a genuine engagement with cosmic endings tends to produce is a shift in perspective on time. Most of us, in ordinary life, think in timescales that span years or decades. We plan for retirement. We think about the lives of our children. Occasionally, we reflect on the arc of a century. These are the natural timescales of human experience, shaped by the length of human lives and the pace of human change. Cosmological thinking does not replace these timescales. They remain the ones that govern our actual lives, but it adds something to them, a sense of the enormous temporal context within which the brief human story is embedded. 13.8 billion years of cosmic history precede this present moment. Hundreds of trillions of years of stellar life remain ahead. Against this backdrop, the urgency that attaches to so many of the things we worry about in daily life takes on a somewhat different quality. This is not a prescription for indifference. The things that matter to human beings, kindness, creativity, connection, understanding, the flourishing of life, do not become less important because the universe is old and vast. If anything, the relative scarcity of complexity and experience in the cosmic story gives them additional weight. The universe does not appear to be overflowing with minds and civilizations. The emergence of consciousness and culture seems, from what we currently know, to be a rare and precious phenomenon against the backdrop of vast stretches of cold, dark, largely inert space. But the shift in perspective that cosmic thinking offers is valuable precisely because it loosens the grip of certain kinds of anxiety. The universe has been here for nearly 14 billion years, working through its processes with patient indifference to urgency. The expansion of space does not hurry. The cooling of stellar remnants does not accelerate on anyone's schedule. Time, on cosmic scales, is abundant almost beyond imagination. There is something genuinely calming about that when it settles in. A second thing that deep engagement with cosmic endings tends to produce is a heightened sense of the present. One of the paradoxes of thinking about the very far future is that it returns you, eventually, to the very near present. When you understand that the universe's active era, the era of stars and light and energy gradients and complex chemistry, is both very long in absolute terms and also finite, you begin to appreciate the present moment of that era in a different way. We live in a universe that is still young. The stelliferous era has perhaps 10 trillion years left to run. The stars have not yet finished forming. Life, wherever it exists, has eons of potential ahead. The conditions that make experience and complexity and science possible are not ending anytime soon. By any relevant measure, we are near the beginning, close to the opening chapters of a story that has barely begun to unfold. And yet, we are here now, able to observe and understand and wonder. We are the universe developing the capacity to ask questions about itself. We are matter organized to the point where it can contemplate its own origins and endings, can build the mathematical frameworks to trace cosmic history from the first second to the last evaporating black hole. That is, when you hold it without flinching, an extraordinary thing. There is a philosophical tradition associated in the modern era with thinkers like Carl Sagan and the cosmologist David Deutsch that finds in the scale and age of the universe not a source of human insignificance, but a source of human significance. Not because the universe cares about us, it does not appear to, in any personal sense, but because understanding the universe is itself remarkable. The fact that beings capable of thought and science have arisen from the same matter and energy as stars and galaxies means that the universe has, in us, developed a way of knowing itself, and that knowing, that understanding, is the rarest and most complex thing we are aware of anywhere in the cosmos. The endings we have explored tonight, heat death, big rip, big crunch, are all endings of the physical universe. They describe what happens to matter and energy in space over vast stretches of time. But they do not tell us everything about meaning. Meaning is not a physical quantity. It is not something that increases or decreases with entropy. It is not something that can be ripped apart by phantom energy or collapsed into a singularity. Meaning is what beings like us make from the physical world we inhabit. It is the interpretation we bring to the facts of existence, the stories we tell about where we came from and where we are going, the values we hold, the connections we form, the understanding we develop and pass on. None of these things require the universe to last forever. They require only that there be time enough to do them. And on this point, the universe has been more than generous. Whether the universe ends in a long, cold quiet, or in the sudden structural failure of the big rip, or in the compressing heat of a big crunch, the time between now and any of those endings is, by every human measure, essentially infinite. The 100 trillion years of the stelliferous era remaining ahead of us contain more time for life, for thought, for discovery, for connection, than we can meaningfully imagine. We are not at the end. We are at the very beginning of the middle. And in that beginning of the middle, we have already managed to understand enough about the universe to trace its probable futures across timescales that would have seemed like pure mythology to every human generation before our own. That is not a small thing. That is, in its own quiet way, one of the most remarkable developments in the 14 billion year history of this particular universe. A third reflection that cosmic endings invite is about the relationship between knowledge and humility. We have spent this entire journey moving between things we know with considerable confidence and things we do not yet understand. The expansion of the universe, the nature of stellar evolution, the second law of thermodynamics. These are well established, tested, reliable. The nature of dark energy, the behavior of quantum gravity near singularities, the existence and properties of any multiverse. These remain genuinely uncertain. Living with that mixture, with confident knowledge in some areas and honest uncertainty in others, is one of the defining experiences of scientific thinking. It requires a kind of intellectual steadiness, the ability to hold what is known firmly without pretending to know more than is justified, and to hold what is unknown openly without collapsing into either false certainty or unnecessary anxiety. The universe, on the longest timescales, is patient. The questions we cannot yet answer are not going anywhere. They will wait for us, or for whoever or whatever comes after us, to develop the tools and the understanding to address them. The universe has been in the business of proceeding without us for nearly 14 billion years, and it will continue to proceed, in whatever direction physics requires, for trillions of years more. Our task, in the time available to us, is simply to understand as much as we can, hold that understanding with appropriate care, and remain genuinely curious about what lies beyond the current edge of the knowable. That curiosity, that patient, persistent, humble wondering, is perhaps the most essentially human response to the vastness of the cosmos. It is what has brought us from the earliest observations of the night sky to the mathematical frameworks of general relativity and quantum field theory. It is what is driving the telescopes and detectors and theoretical efforts currently working on the questions we discussed tonight. And it is what will carry the project of understanding forward, across whatever time remains. We do not know how the universe ends. We have good ideas, well-supported theories, and increasingly precise measurements. But the final answer remains, for now, beyond our reach. And that is all right. The universe is in no hurry. Neither are we. We have been traveling for a long time through these ideas, and this is a good moment to pause and gather everything we have covered before we move into our final reflections. We began this journey by acknowledging that the question of how the universe ends is among the largest questions a human mind can hold. Not large in the sense of being complicated to state, the question is simple enough, but large in the sense that answering it requires us to think across timescales and distances that our intuitions were never designed to navigate. It requires us to take the laws of physics, tested and confirmed in laboratories and observations over the past few centuries, and extend them forward across durations that make the current age of the universe seem like a brief preamble. We trace the discovery of cosmic expansion, the observation, made in the 1920s through careful measurements of galactic redshift, that the universe is not static but growing. Space itself stretches, carrying galaxies apart from one another, not because they are moving through some fixed background, but because the background itself is changing. This discovery transformed cosmology from a largely speculative endeavor into an observational science, grounded in measurable quantities and testable predictions. We explored how the expansion of the universe connects to its origins. Running the expansion backward in time leads to the Big Bang, the origin not merely of matter and energy, but of space and time themselves. The universe has a history that stretches back 13.8 billion years to conditions of extraordinary density and temperature, from which everything we observe has emerged through a long sequence of physical processes: particle formation, atomic nucleosynthesis, the gravitational condensation of the first stars, the cycling of matter through generations of stellar birth and death, the gradual assembly of complex chemistry and biology in the middle chapters of cosmic history. We spent considerable time with dark energy, the mysterious quantity that constitutes roughly 68% of the universe's total energy content and is currently driving an accelerating expansion. Dark energy was discovered through observations of distant supernova in 1998, which revealed that the universe was not decelerating under the influence of gravity, as many had expected, but instead speeding up. The nature of dark energy remains one of the central unsolved problems of theoretical physics. Its most likely behavior, as a stable cosmological constant, points toward heat death as the universe's ultimate fate, but its possible behaviors as a dynamic field that could strengthen or weaken over time open the door to the Big Rip, or, in the case of sufficient weakening, to the Big Crunch. We then traced in detail the long journey toward heat death. Through the stelliferous era, the age of stars that will last another 100 trillion years, through the degenerate era of cooling stellar remnants, through the black hole era, in which the last significant structures in the universe slowly evaporate via Hawking radiation over timescales of 10 to the 100th years, and finally into the dark era, where the universe reaches maximum entropy and the conditions for any physical process have ceased to exist. We explored entropy as the underlying principle driving this progression, the second law of thermodynamics, which requires that the total entropy of a closed system increases over time. The universe began in a state of relatively low entropy and has been working through that endowment ever since. Every star that burns, every reaction that occurs, every process of any kind moves the universe incrementally toward the maximum entropy state that constitutes heat death. The ending is not imposed on the universe from outside. It is the natural conclusion of processes that have been running since the beginning. We then turn to the alternative scenarios. The Big Rip describes what happens if dark energy is phantom energy, a form of dark energy whose density increases as the universe expands, driving a runaway acceleration that grows without limit. In the Big Rip, the expansion of space tears apart the universe on progressively smaller scales in a cascade that culminates in the dissolution of space-time itself at a finite point in the future. The Big Rip would arrive much sooner than heat death, potentially within tens of billions of years, but requires conditions that current measurements do not favor, though they cannot rule out. The Big Crunch describes the opposite possibility, a universe in which dark energy weakens over time, eventually allowing gravity to halt and reverse the expansion. In the Big Crunch, the universe contracts over billions of years, growing hotter and denser as galaxies merge and matter falls inward, arriving finally at a singularity that mirrors in reverse the conditions of the Big Bang. The Big Crunch, unlikely under current models, opens naturally into the possibility of the Big Bounce, a quantum gravitational rebound from the extreme conditions at the collapse point that initiates a new phase of expansion. We considered cyclic cosmologies, theoretical frameworks in which the universe undergoes repeated cycles of expansion and contraction, potentially without beginning or end. The appeal of cyclic models is philosophical as well as scientific. They transform the question of ultimate endings into a question about transition, proposing that every conclusion is also a beginning. Whether cyclic cosmologies accurately describe our universe depends on the physics of quantum gravity at extreme densities, which remains an open question. We acknowledge the genuine limits of current understanding, the unsolved cosmological constant problem, the lack of a complete quantum gravity theory, the measurement uncertainties that keep multiple ending scenarios open. These are not failures, but frontiers, and they motivate the ongoing work of cosmology as a discipline. And in our final chapters, we turn to the human perspective, to what it means to exist in a universe with a finite future, to hold the enormity of cosmic timescales without losing sight of the significance of the present, and to carry the questions forward with the curiosity and humility that this kind of inquiry deserves. All of that has brought us to this moment, to these final quiet minutes of our journey, in which the ideas we have explored settle into a resting place and invite us to simply be present with the extraordinary reality that surrounds us. The universe continues its business as we rest. Somewhere, a star is forming in the compression of a molecular cloud. Somewhere, a red giant is shedding its outer layers in the final stages of its life. Somewhere, two neutron stars are slowly spiraling toward each other across millions of years of orbital decay, destined for a collision that will produce a burst of gravitational waves and heavy elements scattered across space. Somewhere, a galaxy is crossing another in a slow gravitational dance that will take hundreds of millions of years to resolve. All of this is happening right now, at this moment, across the observable universe, and it will continue in one form or another for trillions of years to come. We are very small in this picture. We are also, in our own way, extraordinary within it. And the universe, for all its indifference to any individual story, has provided us with just enough light, just enough time, and just enough physical law to understand something of where it is going. That is the gift that the cosmos has quietly offered, and it is a considerable one. We have come a long way tonight. We began with a simple question: how does the universe end? And we followed it through the mechanics of cosmic expansion, the mystery of dark energy, the long patient story of entropy, the death of stars, the evaporation of black holes, and the three possible conclusions that modern physics offers as answers. We have moved through timescales that began in billions of years and extended outward through trillions, through numbers that required scientific notation to write, through durations so vast that the entire recorded history of human civilization fits into a rounding error at the beginning. And now we arrive at the closing moments of this particular journey, not the closing of the universe, which has much longer to go regardless of which ending awaits it, but the closing of our exploration tonight. A moment to let everything settle, a moment to hold the full picture, as much as it can be held, and simply rest inside it. The universe, as we have seen, carries within its present state the seeds of its eventual ending. The value of the dark energy density, the total amount of matter distributed across the cosmos, the rate at which expansion is accelerating. These are not arbitrary parameters. They are the specific, measurable quantities that determine which of the three scenarios will ultimately come to pass. And they have been fixed, or nearly fixed, since the earliest moments of cosmic history. In a deep sense, the ending of the universe was written into its beginning, even if we cannot yet read that writing with complete clarity. This is one of the aspects of cosmology that makes it feel so different from other branches of human knowledge. Most of the things we study, history, biology, psychology, economics, involve systems that are genuinely open, in which the future is not determined by the past in any simple or traceable way. The universe is different. It operates according to physical laws that are, within the limits of quantum uncertainty, deterministic. The expansion of space follows equations. The behavior of dark energy, whatever it ultimately proves to be, is governed by the same physics that governs everything else. The future of the universe is not a matter of chance or choice. It is a consequence of conditions. This does not diminish the wonder of the universe. If anything, it deepens it. The fact that the cosmos operates according to laws that we, as inhabitants of this universe, have managed to discover and write down and apply, is one of the most extraordinary facts about reality. The universe is comprehensible. It yields to inquiry. It allows itself to be understood, at least in part, by the beings it has produced. Let us take a few moments to revisit the three scenarios we have explored, gently and without the pressure of new information, simply to let them settle as complete pictures. Heat death is the most probable of the three, given what we currently know. It is the ending that follows most directly from the observed acceleration of the universe's expansion and the most straightforward interpretation of dark energy as a cosmological constant. Under heat death, the universe does not come to a dramatic conclusion. It does not end so much as it arrives. Slowly, over timescales measured in the tens and hundreds of trillions of years, at a condition of maximum entropy from which no further change is possible. The path toward heat death is itself a long and eventful story. The stars burn for trillions of years. The last red dwarfs glow faintly in an increasingly dark and empty cosmos. White dwarfs cool over quadrillions of years. Black holes evaporate through Hawking radiation across timescales so enormous they dwarf even these. And then, after the last black hole is gone, the universe settles into the dark era, a vast, cold, nearly featureless expanse in which the occasional photon drifts through emptiness so complete it makes the word empty feel inadequate. In the dark era, the universe has not been destroyed. It continues to exist, in the sense that space continues to expand, and the sparse contents of that space continue to move and occasionally interact at quantum mechanical levels. But the universe has become, for all practical purposes, a place where nothing happens. The entropy has reached its maximum. The gradients that drove all the processes of cosmic history have been smoothed away. The story, for all meaningful purposes, has ended, and yet the universe continues. It is simply a universe without events, without change, without direction. A universe that has exhausted every resource, spent every gradient, and arrived at the deepest rest physics permits. There is something quietly profound about heat death as an ending, once you sit with it long enough. It is the ending that most fully embodies the principle of entropy, the principle that disorder increases, that energy disperses, that the concentrated becomes diffuse. It is the universe completing a process that was underway from the very first moment. Every star that ever burned, every reaction that ever occurred, every mind that ever formed a thought was part of the universe's journey toward this condition. Heat death is not an external fate imposed on the universe. It is the universe completing itself in the only way the laws of thermodynamics allow. The Big Rip offers a different kind of ending, sharper, more sudden, more structural. In the Big Rip, dark energy does not remain stable. It grows. It strengthens over time, driving the expansion of the universe at an ever-increasing rate until that rate becomes infinite in a finite amount of time. In the final phases before the rip, the accelerating expansion tears apart the universe on progressively smaller scales. Galaxy clusters, galaxies, solar systems, planets, atoms, nuclei, until space-time itself reaches a singularity and the fabric of the universe comes apart entirely. The Big Rip is, among the three scenarios, the one that most challenges our intuitions about the stability of physical reality. We tend to think of the structures around us, planets, stars, the very atoms of which we are made, as fundamentally solid, as things that persist unless acted upon by some external force. The Big Rip tells us that space itself can be a force of dissolution, that the expansion which has been carrying galaxies apart since the earliest moments of the universe can, if it grows without limit, dissolve every structure that exists. Whether this will happen depends on the true nature of dark energy. Current measurements favor a cosmological constant over phantom energy, which means the Big Rip is currently the least likely of the three scenarios. But the measurements carry uncertainties, and phantom energy cannot be ruled out. If future observations tighten the constraints on W and find values consistent with phantom energy, the Big Rip would become a genuine possibility, and the timescale of its occurrence could be estimated with increasing precision. For now, we hold the Big Rip as a genuine possibility, a reminder that the universe has surprises left in it, that dark energy is not yet fully understood, and that the accelerating expansion we observe today might be the early phase of something far more dramatic than we currently expect. The Big Crunch is the most symmetrical of the three endings, the one in which the universe's history forms a kind of arc, beginning in a hot, dense state and returning, after a long interval of expansion, to a hot, dense state. In the Big Crunch, dark energy weakens or disappears over time, allowing the gravitational attraction of matter to gradually slow and then reverse the expansion of the universe. Galaxies drift back together. Temperatures rise. The universe contracts toward a final singularity that in many ways resembles, in its physics, the singularity from which it emerged. The Big Crunch is the least likely of the three scenarios under current models, because it requires dark energy to weaken in ways that are inconsistent with its most natural interpretation as a cosmological constant. But it is not ruled out. If dark energy is a dynamic field that diminishes over time, the Big Crunch becomes possible. And if it is paired with a bouncing mechanism, if quantum gravitational effects prevent the formation of a true singularity and instead produce a big bounce, then the Big Crunch is not an ending at all, but a transition, a doorway between one phase of cosmic evolution and the next. The cyclic universe that the Big Bounce implies is one of the most intellectually appealing ideas in cosmology, precisely because it dissolves the question of ultimate endings. If the universe bounces, if every contraction seeds a new expansion, then the question of how it all ends may have a very simple answer. It does not. It cycles. It has always been cycling and will always cycle, in an unbroken sequence of expansions and contractions that neither begins nor ends in any final sense. We do not know if this is true, but we know it is possible, and the possibility of a universe without ultimate endings, a universe that simply continues through different phases across infinite time, carries its own kind of peace. As we settle into the final minutes of our journey tonight, let us spend some time simply dwelling in the scale of what we have been exploring. You are resting somewhere on the surface of a planet that formed about 4.5 billion years ago, from a cloud of gas and dust that itself formed from the remnants of earlier stars. The atoms in your body have been part of stellar interiors, interstellar clouds, and countless other configurations over the course of the universe's history. In the most literal physical sense, you are made of the universe, assembled from material that has been present, in one form or Another, since the first minutes after the Big Bang. The Sun, whether or not it is currently visible, is a middle-aged star about halfway through its main sequence lifetime. It has been burning for about 4.6 billion years and will continue for another 5 billion before expanding into a red giant. The nearest star to our Sun, Proxima Centauri, is about 4 light-years away, so far that its light takes 4 years to reach us. The Milky Way, the galaxy in which our solar system sits, contains between 200 and 400 billion stars. It spans about 100,000 light-years. On clear nights, you can see a small portion of it as a faint band across the sky. The combined glow of hundreds of billions of stars, most of them individually too faint and too distant to distinguish. Beyond the Milky Way, the observable universe contains an estimated 2 trillion galaxies. Each contains hundreds of billions of stars on average. The total number of stars in the observable universe is estimated at around 10 to the power of 24, a number so large that any attempt to visualize it dissolves into pure abstraction. All of this, all 2 trillion galaxies, all the stars they contain, all the planets, all the dark matter and dark energy that pervades the space between them, exists within the universe we have been exploring tonight, a universe that began 13.8 billion years ago, that will continue for at minimum tens of trillions of years, and that will end in one of 3 possible ways, depending on a property of dark energy we are still in the process of measuring. We are a very small part of this universe, but we are not an insignificant part. We are the part that knows about the rest, the part that has developed the mathematics and the instruments to trace cosmic history from the first second to the last evaporating black hole. We are the universe's capacity for self-knowledge, brief and fragile and remarkable. The question of how the universe ends is one that human beings have been asking in various forms for as long as we have been human. We have asked it through mythology and religion, through philosophy and poetry, through mathematical physics and observational cosmology. Each generation has taken the question further than the last, has developed new tools, made new measurements, extended the reach of theoretical understanding into territory that was previously inaccessible. We do not yet have the final answer. We may not have it for a very long time. Perhaps not until the theoretical and observational tools of a future generation allow a precise determination of dark energy's nature, or until a complete theory of quantum gravity illuminates what happens at the extreme conditions associated with cosmic endings. But we are much closer than we were a century ago, and much closer than we will be a century from now. The universe is patient. It will be here, in one form or another, for whatever time it takes for the inquiry to mature. Meanwhile, we are here too, at this particular moment, in this particular sliver of cosmic time, carrying the question forward with the tools and the understanding we have. That is enough, more than enough, really. It is the work of a species that has looked up at the night sky for hundreds of thousands of years and refused to stop asking what it all means and where it is all going. We do not need to know the ending to appreciate the story. The story is, in every way that matters, already magnificent. The expansion of the universe continues tonight, as it has every night since the beginning. The stars burn, the photons travel. The black holes accumulate mass with patient indifference to any urgency. The entropy of everything, everywhere, increases by its tiny and inevitable increment. And on a small blue planet near the edge of an ordinary spiral galaxy, a collection of matter that has organized itself into something capable of thought and curiosity and wonder drifts gently toward sleep, carrying inside it in the only place such things can be carried, a slightly larger understanding of the universe it inhabits. That is a good way to end an evening. The cosmos is vast beyond any comfortable measure, old beyond any convenient comparison, and headed toward a future that will unfold across timescales that make our entire civilizational history seem like the briefest of openings. Whatever ending awaits, the long quiet of heat death, the structural dissolution of the Big Rip, the compressing heat of the Big Crunch, or the transition of a big bounce into something new, it is far away, and there is much to observe and understand and experience before it arrives. For now, the universe simply is, expanding, evolving, aging at its own measured pace. And if you are already drifting toward sleep, that is exactly as it should be. The universe will still be here when you wake. The questions will still be here. The stars will still be burning.